Hey everyone, welcome to this Friday live discussion as part of your daily equation. Glad you had a chance to join me here for our little conversation. Those of you who have been here on previous Fridays know that sometimes little is very much in the eye of the beholder. It is absolutely not absolute. It is certainly one of the words of relativity. I don't know how long we'll go today, but if the past is any guide, we may be sitting here for a while, which can be fun. I've certainly enjoyed the discussions that we have had. And let me just quickly also note that I think, as I mentioned last time, as I head into next week, I begin to teach back at Columbia. I'll be teaching a course there in the summer. So it's going to be more difficult for me, together with a bunch of other things that we're doing. Some of you have also asked about World Science Festival, the regular programming that we do. We're going to start rolling those programs out over the next few weeks. So there's obviously a lot of effort and time that goes into putting those together. So your daily equation, the word daily may also be relative. I will continue to do some of the episodes, but I won't be able to do them at the same frequency, I don't think, as I've been doing them before. But we'll play it by ear. So just if you have a little patience with me, flexibility with the rate at which we create them, that would be great. All right, so let's get into the discussion here. And I realize that I've got the wrong chat window open, so let me just fix that so I actually see. Yeah, I think this is the right one. Justin Atienza says, "Sup, chat." I think that means that I'm on the right page if I'm not thinking about things wrong. Good. Okay. So there was one question that caught my eye. Yeah, there it is. Andrew Haney asks, is it right to say that reality is not absolute since what's real differs with different perspectives? And that is a subtle question. What I would say is there are certain qualities of the world that are absolute, in the sense that, in a very specific sense, that anybody who is following a particular procedure to measure or observe or quantify certain aspects of the world around us will get the same result. For instance, if you're talking about the electric charge on the electron, or the mass of an electron, anybody who is using the appropriate equipment in the right manner, regardless of where they are, say, on planet Earth, or as far as we can tell, regardless of where they are, throughout at least the observable universe, we believe that they will get the same value for the electric charge of an electron or the mass of an electron. So those qualities of reality do seem to be absolute in the sense that everybody agrees on them. In Einstein's relativity, there are other qualities of the world that we believe to be absolute too. In fact, you may be surprised to hear, and I'd be interested to know if you're surprised to hear. I mean, look, those of you who've read popular physics books or know the subject well know exactly what I'm about to say. But for those of you for whom this material is new, Einstein didn't want to call relativity theory relativity. He wanted to call it invariance theory, invariant, the things that don't change. You see, because the right way of thinking about, say, the special theory of relativity is not that Einstein made everything relative. Like, you hear people say that kind of silliness a lot. And if it's tongue in cheek or if it's just meant in a colloquial sense, fine. I mean, use language however you want in everyday life. But when you're talking about the precise description of Einstein's special theory of relativity, it's not that everything is relative. What Einstein showed is there are qualities of the world that in the past we thought were absolute, and those qualities of the world turn out to be relative, space and time being the great examples. But he also showed that there are other qualities of the world that are absolute. They're just not the qualities that previous generations thought to be absolute. For instance, if you have two events that take place in the universe, a firecracker goes off over here and then another firecracker goes off over there, you can think about the distance between them in space, how far apart the events took place. You can also think about the distance between them in time, the time difference between them from your perspective or from anyone's perspective. Different observers will disagree on the spatial separation between those events and the temporal separation between those events. However, and here's the beautiful thing, Einstein shows that there's another quality, another quantity, depending upon space and time, that everybody will agree on. And in units where the speed of light is equal to 1, that quantity is delta t squared, the time difference, according to any observer, squared, minus delta x squared, the spatial separation squared, according to any observer. So that particular combination of space and time is something that everybody will agree on, regardless of how they're moving, regardless of the configuration in which they find themselves relative to the events that they are witnessing. So there you have it. There is an absolute quality of the world. It's just not the qualities that we thought to be real. So I would say, in answer to the question, that there are absolute qualities of the world. Reality is something that's out there. There are many features of reality that are in the eye of the beholder, both metaphorically, poetically, and scientifically. But there are other qualities of reality that everyone will agree on. And I think they have every right to be called the absolute qualities of reality. Okay, so that was a long answer to our first question. So anybody who's still with me after that one, let's see what else we can get to here. All right, from Kuwait, great to see you guys. From Vancouver, Canada. I'm scrolling. Pakistan, California. Yeah, do tell us where you all are coming from in the chat here. Oh, here's one. And many people have been asking me this question, so I think I should dispense with it right now. There was a report that you may have seen that NASA has found evidence of a parallel universe where time goes backwards. Anybody see that particular news report? And so a lot of people have asked me, well, okay, is that really true? What does that really mean? And here's the situation. So there were some observations that have been made of certain cosmic ray particles. What are cosmic rays? You know, the sun emits particles that travel through space. They hit our atmosphere. They cause various kind of interactions to take place, and showers of particles rain down from the sequence of processes that I just described. And some of the folks who were investigating these down, I guess it must be at the South Pole, a particular experiment called Anita, they found a strange result. They found a result. It was actually, I think, way back in 2016. So it's not a new result. It's just people are really thinking about it and trying to understand it. And they found what seemed to look like the showers going up as opposed to down. And that was quite confusing, and it's hard to make sense of that. And many people have put forward ideas. For instance, maybe some of these particles that they are observing somehow were produced by the ice and they're going that direction as opposed to coming at us from space and so forth. So the bottom line is many people have tried to come up with explanations for the data. And my understanding, I've not actually gone through the papers myself, but my understanding is that none of those explanations really are yet convincing. So it's an anomalous observation, which is not all that infrequent in science. It's one that's been around for a handful of years. And when you have difficulty explaining an anomalous observation after a couple of years, some of the more far out explanations begin to bubble up to the surface. And one of the farthest out explanations is that we are witnessing particles in a parallel universe that, relative to our orientation of time, are traveling backward in time, and therefore they're going in the wrong direction, explaining the weird observations. So do I consider that to be evidence for a parallel universe? Number one, I don't. I consider it that's an interesting explanation. I'm glad it's on the table. I'm glad people kick it around, but it's going to take a lot more than that to convince me. And I'm open to these ideas. I wrote a whole book on parallel universes, the hidden reality, right? It's all about different flavors of parallel universes. You have to be very careful when you claim that you've got evidence for something so radically distinct from established science. And it's going to take a mountain of observational experimental data to really convince us of the possibility that these parallel universes are real, or that this particular explanation is the one that we should take seriously. Bottom line is, Carl Sagan perhaps said it best. I don't remember the exact wording, but something like extraordinary claims require extraordinary evidence. It's a great quote, right? The notion of a parallel universe where time runs backward is an extraordinary claim. It will require extraordinary evidence, and we do not have that extraordinary evidence in hand. Now, sociologically, culturally, the second certain publications hear of the possibility that scientists may at least be considering the possibility of parallel universes with particles traveling backward in time, they kind of tend to forget about all of the caveats and all the other explanations that people are kicking around and focus only on that. And then the word spreads outward. So I don't like to throw cold water on excitement, but I do have a certain resistance and a certain allergic reaction to the hyperbole and the over the top headlines and the grand excitement about some far out sounding idea, because then when it's not true, people roll their eyes later on when there is some extraordinary claim and it is something that people really are taking seriously. And I would say that the vast majority of physicists are not at the moment coming to the conclusion that the headline that I certainly read in one of these articles, that NASA finds evidence of a parallel universe where time runs backward. You ask most physicists in the world today, and they will not say that that summarizes their perspective. All right, so Dom Casimiro said that was too long an answer. All right, Dom, I will try to speak faster or use less words going forward. Thank you for your constructive criticism. But right below you, someone said, "Love you, Professor." So maybe there are multiple perspectives on how much information I should give you. But whatever you want to ask, I'll do my best to answer it as concisely as possible. All right. So what else do we have here? I got to take my finger off the scroll. All right, Maximilian Egger says, "What would be evidence for such a claim then?" Yeah, that's a very good question. And well, first of all, you want to make certain that the data is real. So you want to make certain that this is not some one-off, perhaps anomalous experimental error, right? You may recall that there was claims some years ago that particles were traveling faster than the speed of light. And it was an experiment where particles, neutrinos, were being shot through rock from one location, Gran Sasso, Italy. I think it was from CERN to Gran Sasso, Italy, and the particles were arriving too soon, right? And so there were these claims of faster than the speed of light. The speed of light limit has been broken. That speed limit has been broken. And most of us said to ourselves, I don't trust that. Relativity, it's been around so long. Anything that violates it, it's going to take a mountain of experimental evidence to support it. And when the experimenters went back and checked the equipment very carefully, they found that there was a problem with the equipment. And when they fixed the problem with the equipment, the data went away. So that's number one. You want to make sure that this is replicable experimental data that you see at a sufficient frequency, that you can really gain some statistical confidence that this is not just some weird anomaly with either the equipment or some kind of other fluke in the environment. And when you rule out every single possibility of a sort that is closer to our perspective on the world than parallel universes where time run backward, then you get to a place where you start to take it seriously. We're not there yet. All right, so let's see. There's one question I think I understand, but no, maybe it's an internal conversation, so I'm going to let that one go. Let's see. Garden asks, "Isn't it crazy how time breaks down at the beginning of the universe? Is it because time and space work together?" And well, partly that is the answer. Again, the lesson that we learned from Einstein is that the Newtonian perspective that space is one thing and time is another, that is a perspective that needs to be jettisoned. And we learn that space and time, more or less as you described, Garden, are kind of woven together. That's why we use the language, the fabric of space-time, as if they're woven together in a particular pattern dictated by the equations of relativity. And when you go back in time with your mathematics, not for real, but you use your equations to turn the cosmic film ever further back in time, what you find in our understanding of the universe is that the density of matter and energy gets higher and higher. And when the density, as you head back toward the beginning, soars toward the number infinity, that's basically what the math tells you, you realize that it's not just that sort of time is breaking down, it's that our whole mathematical architecture for understanding what happens in the earliest moment of the universe, that is breaking down. You know, sometimes, I think I said it before, people have a sense that the word singularity is some mysterious concept, some beautiful mysterious, the singularity is coming, the singularity is near, right? And depending on what you mean by that, it can have a real meaning. I'm not trying to denigrate some of the folks who speak that way, but the bottom line is, in physics, when we talk about singularity, it is a euphemism, it is a metaphor, it is a word that actually tells us that we don't know what is going on. Singularity means math breaks down, we don't know what's going on. So it's not that we can really say that time stops at the Big Bang. We can't say that time begins at the Big Bang. These are all real possibilities. But what we can say is we don't have the math to give us insight into what happens at time zero. And until we have equations that do not break down under any circumstances, however extreme the environment may be, however dense the energy might be, then we are at a loss. So we need those equations that will never break down under any circumstance. We hope to one day have them, but I would say at the moment we are lacking that kind of technical understanding, and that's what prevents us from saying what happened at time zero itself. Ludwig von Beethoven, a regular on this discussion. Professor, me and some others have now a subreddit called Your Daily Equation with an R, a Reddit / Your Daily Equation, to discuss topics discussed here or to ask for additional questions. Do you approve of this initiative? Yeah, sure. Why not? I love conversations about the things that we are focusing on. And Ludwig, I might also mention to whoever is interested, sorry, I just took a shower and I think I got water in my ear. I'm going to be doing a semi-regular Reddit discussion, conversation, Q&A. You may know that Reddit has this thing called RPAN, Reddit Public Access Network. I did it a couple of weeks ago. It was kind of fun. A lot of people were discussing the kinds of things that we discuss here. So I think that's going to be Fridays from 2 to 3, maybe every other week. So I don't know how long we'll continue our live sessions, but for at least a while, you can join me at 2 o'clock on that Reddit Access Network. I'm sure you guys can find it. I don't even know where you go find it. And but yes, of course, anything that you guys want to do to continue the conversation, that's fantastic. All right. Gayatri Pandit asks, Professor, why does string theory require 10 or 11 dimensions? And does having different dimensions mean different universes or shapes of objects? And I wish I could give you an answer for why string theory requires 10 or 11 dimensions, in the sense of why 10 or 11. I think I may have mentioned before, I've never been able to come up with anything but the mathematical explanation of that. So let me just frame it this way. There is an equation in string theory which has to be satisfied for the theory to be mathematically coherent. If this particular equation is not satisfied, you can prove that all sorts of weird things would happen, which would destroy the viability of the theory. You'd lose energy conservation. You'd lose all of the essential details that make a mathematical theory of the universe viable, worthy of attention. In this equation, in some sense, it counts the number of vibrations of a given energy of a vibrating string. If a string is vibrating, say, in just the plane, in your mind, you can picture there are just so many distinct vibrational patterns that it can have. If you go to a third dimension, now there are more distinct vibrational patterns of a given energy, because not only can it vibrate this way, the string can also vibrate this way. And it's harder to picture, but if you go to 4 dimensions of space, there are yet more vibrational patterns that are accessible. 5 dimensions more, 6 dimensions more, and so forth. So here's the thing. When you calculate the number of vibrational patterns necessary to solve that equation that I mentioned a moment ago, there aren't enough vibrational patterns in 2 dimensions of space, in 3, 4, 5, and 6, and so on. Only when you get to 9 dimensions of space and 1 dimension of time are there enough vibrational patterns to satisfy that equation. I cannot convince you of the number 9 spatial dimensions, but I hope it gives you the flavor of reasoning that connects the number of dimensions of space with the viability of the theory. It's not that someone's sitting there and say, wouldn't it be fun to have extra dimensions of space? People did follow that approach way back in the early part of the 20th century. Kaluza, Klein, they weren't being as facetious as that, of course, but they were examining the possibility of extra dimensions just because it was an interesting possibility. And they were curious to see whether physical law could make sense in a world with extra dimensions. And they found some very interesting results. That's not what happens in string theory. In string theory, you do not posit the extra dimensions. In string theory, you study the fundamental mathematical equation of a vibrating string in an existing space-time arena, and you find that that space-time arena must have more than 3 spatial dimensions for the fundamental equations to be internally consistent. That's a completely different way of getting to this idea of extra dimensions of space, and that's why it's much more convincing. Finally, to end this answer to this question, when you go to M theory, this more refined version of string theory, you learn that the approximations that we had been making in conventional string theory left out 1 spatial dimension. They were insensitive to 1 spatial dimension, and therefore 9 dimensions of space went up to 10 dimensions of space, with time takes us to 11 space-time dimensions. So that's the chain of reasoning. And some of you have asked me in one of these episodes to explain this curious fact, that 1 plus 2 plus 3 plus 4 plus 5, what does that add up to? Someone just tell me in the chat. I'm sure some of you guys know what that adds up to. And infinity is one answer, and it's a fine answer, but that's not the answer that I'm looking at. I'm looking at a finite answer for adding up all of the numbers. And I think there's let me just see if I can see if anyone has that answer for me. Well, I'm waiting. Maybe it will come in. I think there's a bit of a slight time delay between when there it is. Thank you. Walking Android, -1/12. Thank you, Walking Android. And so people wanted me to explain how it could be the real flunon -12. How it could be that 1 plus 2 plus 3 could add up to -12. And at some point I will do that. But that -12, it turns out, is one of the key ways of understanding how it is that string theory requires the extra dimensions that it does. Now, a lot of people, I guess that's the bit of a time delay between what I say and when you hear it. So I see many people, while coming in with -12. Wow, you guys are good. How many of you who know that the answer is -12 think you really understand why it comes to -12, or you can give the argument? I'd be interested to see your answer on that. Just say yes if you understand it, and no if you're a little bit shaky on it. But the reason I ask this is because this is deeply connected to the technical explanation for why there are extra dimensions in string theory. So that's the kind of thing that we would need to cover in order to give a full answer to the extra dimensions in string theory. Okay, I see a lot of -12s, and some are saying that they understand it, and some are saying yes. And Ramanujan is no, Dad, teach us, says Justin. And in a subsequent episode, I will not try to do it now. I know it's -12, and I know how this comes about. Yes, great, perfect. So some of you are quite advanced, which is fantastic. Some of you are saying that you don't. Okay, so I'm going to jump over to a different question now. John Smithy asks, how do you derive the time that inflationary expansion occurred for? And you may recall in the episode, which episode was it? I think it was the last one, number 30. Well, that was an inelegant sip of water. I'm so glad that that's on film. So in the episode number 30, I described how this burst of repulsive gravity, this inflationary expansion, just lasts for a tiny fraction of a second. And I said it was something like 10 to the minus 32, 10 to the minus 33 seconds. And the question is, what determines the duration of the inflationary burst? And the answer is it's nothing fundamental. So you may recall that I put an inflationary potential, V of phi is what I called it. And V of phi, I won't bother drawing it, but you recall it was a very gentle slope, and then it had a steeper section to the curve, and that ensured that the value of the inflaton field would stay pretty constant for a while. And it's that constant value of the energy and pressure densities that yields the repulsive gravity that pushes everything apart. But then the inflaton rolls down the field. So the question is, how long does it stay on the top part, which is the span of time during which the inflationary expansion takes place? And that's totally dependent on the slope of that top part and the length of that top part, right? It's V of phi. So how much does phi have to change before it hits that other part of the curve in which it falls down? And all that's chosen by hand. All that's chosen by the physicist. All that's chosen by the definition of the model. And once you choose that definition of the model, you then work out how long the field stays up on the hill. And I noticed that half of my head's being cut off, so I'm going to shift this a little bit. So that's really the answer to the question. We would love it if we had a fundamental explanation where you could say from first principles, here's what the potential looks like. From first principles, here's how long the field therefore will stay on that plateau. From first principles, therefore, here's how long the inflationary burst will last. And we can't do that yet. So that's a goal for the future. Maybe one of you guys will figure out how to do that. But as of today, it's all set by hand. It is not set by any fundamental principle. Okay. Yatish Argawal, loved you in Star Talk. Sir, could there be a component of the Higgs field in the time dimension, which is why we only travel forward? Wow. Well, first, Yatish, thank you for the kind words on that Star Talk episode. It was a lot of fun talking about the end of time with my friends over there at Star Talk, Chuck and Neil. But your question is an interesting one, a perplexing one. So when we talk about the Higgs field, we do talk about it filling space for a duration of time. So it really does fill a region of space-time. So I think you may be imagining that the Higgs field only talks to space and it doesn't have any conversation, if you will, with the temporal, the time direction, but that's not true. So for instance, it's possible in the very early universe that the Higgs field did not fill space. There are many, in fact, the most common models imagine that when you heat up the universe sufficiently high, the Higgs field evaporates, it goes away. So the early universe was so hot that in many of these models, there was no molasses filling space. There was no Higgs field filling space, which means at that moment, all the particles would have been massless. And then as the universe expands and cools, the idea is that the Higgs field can condense, kind of freeze out, if you will, from the evaporated environment. And then from that point forward, space is filled with the Higgs field. So if you think about it that way, I think you'll recognize that the Higgs already fills space and time in this very specific way that I described. So we're not missing that possibility. If I didn't interpret your question correctly, do ask it again, but I hope that addresses it. Um, ooh, what happened? I went away for a minute. I I must have disappeared for a minute, folks. I have no idea if you heard my answer. I just gave one of the best answers of my life, and I hope that no. I assume that you guys heard it. I don't know what happened, but anyway, I think we're back in business here, which is good. Marin Kuyud Ku. I'm going to get this. Kukendall. Marin Kukendall. I loved your new book. Thank you. I appreciate that. Always like kind words. Well, you're thinking about the end of our universe and the far, far future change if there were proof of other universes. And to some extent, it would affect my thinking. You may recall, and it was only a brief mention, but in chapter 10, I think it was chapter 10 toward the end. Yeah. In chapter 10 toward the end, I do note this interesting possibility that the wonderful, creative, influential physicist Alexander Vilenkin and his collaborator came forward with some years ago, where they imagined the possibility that as our civilization, or more generally, our universe comes to an end, maybe we could pack up all of our knowledge and insight into some kind of capsule and launch it into another universe if the multiverse were real, sort of send it out in space and it could reach sufficiently distant locations where those regions would not suffer the same fate that we might be suffering. And that's an interesting possibility. It wouldn't change my view on how reality would end in our universe, the part that we have direct access to, and the environment that we have been living within and measuring and having a civilization on planet Earth and so forth. But at least conceptually, the idea that we might launch our understanding into a distinct realm that might last longer than us at least gives us some kind of symbolic carrying on. I was going to say symbolic immortality, but that's not quite true because that other region will also have a finite duration. And what they showed, though, and this is the part that is perhaps curious of all, if there truly is a multiverse, then you can argue that there is some region, in fact, many regions out there, that will last arbitrarily long through weird quantum fluctuations that cut against the grain of the likelihoods given by the probabilistic mathematics. If something has a 1 in a million chance of happening, if you have enough universes where every possibility takes place, then clearly there's going to be some universe in which that 1 in a million weird possibility happens. And sometimes the 1 in a million or 1 in a billion or 1 in a trillion weird possibility is such that it will extend the duration of life and consciousness in that universe. And yeah, so that definitely slaps your brain around a little bit. Maybe gives you a little bit of comfort that even if life and consciousness come to an end in our universe, there's some place, it's very abstract because you don't have direct access to it, but there's some place out there where life and mind continue. So do I take solace from that? I don't know. Number one, I am a multiverse skeptic. Some people are like, "Well, what are you talking about, man? You're the guy who's always talking about other universes." I talk about other universes as an interesting possibility. I wrote a book about it because I find that possibility exciting, interesting, worthy of attention. But in that book and in any interview where they don't cut out the caveats, I always say we need evidence, we need observation to establish that these ideas are correct. At the moment, I view them as a powerfully interesting tool in our toolkit as we try to understand things in the world around us. So, with the recent observations of those strange particles, sure, bring out your toolkit and imagine the possibility of other universes. But I'm a skeptic of this. So, in terms of taking solace from this idea, it feels too tentative for me to hang any existential hope on the continuance of life and mind in a parallel universe. So it doesn't really help me in that regard in any deep way. Rather, the approach I take in the book does help me, when I recognize how unlikely it is that we're here, when I recognize how spectacular it is that particles governed by physical law can do the things that we do, that to me lessens the blow of realizing that life and mind in our universe are finite. That's what works for me. Thank you for the question, though, of course. All right, what else do we have here? Ashik Rial asks, Professor Greene, please explain the equivalence principle. Well, yeah, and then the question about particles accelerating in space, creating curvature and so forth. Yeah. See, the equivalence principle is the heart of Einstein's general theory of relativity. The way that I like to think about it is that a sufficiently well chosen accelerated trajectory can either mock up a gravitational force or cancel a gravitational force. The example that I gave in one of the earlier episodes, I can't really do it here. You know, I did this thing with a bottle of water. This is glass. Somebody got mad at me for having plastic bottles last time, so I listened to you guys. So here is a glass bottle, but imagine it had holes in it, which you can do in a plastic bottle. If the water, therefore, would be spraying out of the holes if I'm holding it like this. And I noted, if you recall, that if you let this go into free fall, accelerating downward from my perspective, then that is able to cancel out the pull of gravity on the water, so the water stops spraying out of the holes. Accelerated motion canceling out the force of gravity. Einstein's version of this was the painter who fell off a ladder, and while descending in that accelerated trajectory from our perspective toward the surface of the earth, that painter doesn't feel his or her own weight. Right? If the painter's on a scale, the scale falls with the painter's feet, so the painter's no longer pressing down on the scale, and so the reading on the scale goes to zero. So that's beautiful. That's a beautiful unexpected link between accelerated motion and gravity. In this case, accelerated motion canceling out gravity. And what Einstein emphasized, and I described in an earlier episode, the reverse is also true. Accelerated motion upward, say in space, if you're standing, say, on a platform and someone accelerates things so that the platform is pushing up against your feet, if the acceleration is the right magnitude, you'll think that you're standing on planet Earth. It'll feel like the force of gravity. So it's this equivalence between accelerated motion and the force of gravity. And this is what was critical to Einstein being able to work out the general theory of relativity. Now, something occurred to me as we were talking about that. Oh yeah, here's the point that I wanted to make. So oftentimes we talk about Newton and the apple, right? Newton is sitting under the tree, the apple falls, hits him in the head. And the idea is that that kind of inspires, or at least as the story goes, that inspired Newton in understanding the force of gravity. In the Einsteinian description, it's completely different, right? The Einsteinian description, the state of free fall is the natural state of existence. That's the one where the body doesn't feel a gravitational force. The painter does not feel his own weight or her own weight or their own weight during the descent. The water doesn't come out of the holes of the bottle because the water no longer feels its own weight. So the natural state of being is free fall. And therefore, the natural perspective in the apple hitting Newton on the head is not Newton's perspective. He's not in free fall. He's on planet Earth. He's not falling. It's the apple's perspective. So the story of the Newton apple from the apple's perspective is the apple detaches from the tree accelerates upward, the apple looks down and sees Newton's head approaching it, and Newton's head slams into the apple. That's the description of that famous story from the more natural perspective of the body in free fall, which in this case is the apple. Okay, carrying on. Andre Alex says, so that means we are all gods. I'm not sure gods what. So if you want to clarify that, I'd be happy to answer it. Prayog Dash, who's also here as a regular. Thank you, guys. I'm happy to see the regular participants. Your podcast and Star Talk was really knowledgeable. Thank you. But I have a doubt. Can we interpret the notion of quantum entanglement to the stitched fabric of space and time? So look, Prayag, you should have a doubt. Nobody right now is saying that we really understand what the fabric of space-time is made of. We use the language all the time. Einstein either used exactly that language in the German, perhaps, or something equivalent. This notion that there is a stuff out there that can warp and curve, and using the idea of a fabric is a nice poetic way of talking about it. But what really is the fabric made of? People have asked that for a long time. And what I find exciting is that at least now we have some proposals, some strategies for how to go about addressing that question. And quantum entanglement is one of the most fruitful strategies that have been pursued. Again, quantum entanglement tells us that distant particles are connected, if they're set up in the right way, with kind of threads of quantum entanglement. In an earlier episode, I made them these yellow threads, or I didn't make them these yellow threads. Josh Zimmerman made them these yellow threads, who's actually behind the scenes right now, making sure that all of this is working. Spectacularly creative editor and animator. But anyway, so we have these yellow threads between the particles, and that allows them to correlate their behaviors. Now, when you think about that, distant particles connected by a thread of quantum physics, you begin to wonder, could it be that space itself is stitched by these threads of quantum entanglement? And there is now mathematical might behind that idea. People like, many people have been involved in this idea, from Lenny Susskind to Juan Maldacena, Mark from Ramsdock, many people. We had a full program at the World Science Festival. So if you want to have a disc, and you know what, we're going to do it again, a more refined version of that program this summer. We're going to have a program on quantum entanglement and wormholes and stitching the fabric of space-time. So we'll go into it in much more detail there. But I would say, Prayag, that having doubt that that is the right way of thinking about space, that it is a fabric stitched by the threads of quantum entanglement, have doubt, but have an open mind, and let's allow the research to progress, and let's see where it goes. Because honestly, I'm shocked that we even have ideas that are sufficiently well formulated for mathematical analysis regarding the fabric of space-time, what it's made of. I wouldn't have thought that in my lifetime, frankly, we'd be able to make progress on that. And the fact that there are some real interesting possibilities that people are pursuing, that to me is the big story. Whether it's the right explanation, I don't know. But the big story is that we can actually begin to address these questions with a degree of mathematical seriousness. And that's very, very impressive. So let's see. So a couple of people are asking about wormholes, maybe because I mentioned it. Abu Bakr Farouqui asks, Professor Greene, what's the likelihood of the existence of intergalactic wormholes? And then right underneath that, Gayatri Pandit asks, do you think quantum entanglement can make traveling through wormholes possible? All interesting questions. Number one, there is zero evidence for the existence of any wormholes whatsoever. No evidence. All right. It is an idea that naturally emerges from Einstein's general relativity. You can solve the field equations with certain assumptions and come up with these shapes that have this tunnel-like quality, this throat-like quality. Einstein himself, in a paper with Nathan Rosen, 1935, wrote down one of the early solutions of this form. So the math allows for it. Does that mean that these entities are real? Well, you remember what Einstein said to Lemaitre? Your calculations are correct, but your physics is abominable. He was talking about the expanding universe in that example, and there Einstein was dead wrong. Physics was not abominable. Now you could say the same thing about wormholes. They naturally come out of calculations entrenched within the general theory of relativity, but not every mathematical solution is realized in the real world, I think. And therefore, you have to have real observational evidence, and we do not have any. Now, could quantum mechanics help make wormholes traversable? And the answer to that is yes. So when you create mathematically a wormhole, you then often investigate its properties, and scientists have found that they tend to collapse in on themselves, such that it would be very difficult, if not impossible, for something to pass through. However, people have found that if there's an exotic form of matter that has a negative energy density, excuse me, ate too much for lunch, negative energy density, then that matter can create an outward force that can keep the throat, the tunnel part of a wormhole open. And that yields what's known as a traversable wormhole. Now, again, we don't know if wormholes are real, so we don't know if traversable wormholes are real, but at least the math does allow for quantum mechanics to yield a kind of substance that would keep a wormhole propped open. So a lot of tentative things in that sentence, but the bottom line is, at least mathematically speaking, I don't know if this is in the real world, you can in principle have wormholes that would be traversable, that you could pass through. And that's pretty exciting, because if you had a traversable wormhole, you can turn it into a time machine. You move the openings of a traversable wormhole relative to each other, put one near the edge of a black hole, one far away. Time elapses at different rates at the two openings of the wormhole. Imagine you have a tunnel with two openings, and you're somehow able to make time elapse at different rates at the two openings of the tunnel. That means as you pass through the tunnel, you'll start at one moment in time, but you can end up at a very different moment of time, either in the future or in the past. And that's why these ideas are shocking and strange. Some would say that's proof that you'll never have a traversable wormhole, because you can't travel to the past, some would say. I think it's too quick, but nevertheless, it would be monumental if there's any real evidence for any of these wormhole ideas to be actually real. Marilyn Kozak, so many questions, but hoping your back is feeling better. Marilyn, thank you. You must have seen the interview with Joe Rogan, where at the end he nicely inquired, I guess, why I was sitting at such a strange angle. No, we'd spoken about it beforehand. That's what it is. Of course, I showed up there in crutches. Now it's all coming back to me. And so Joe had various suggestions. In fact, he actually took me after the interview to his workout stations right in the same space where we did the conversation. And he put me on all sorts of machines. And I have to say, that was the beginning of the road to recovery for me. And he also suggested all sorts of treatments. It was really great, really nice guy. But yes, the answer is my back is feeling much better. So, you talk about, a life of contemplation, thinking about the universe and math and physics. If your back is hurting or you've got any physical ailment, it all goes away. You can't do anything. You can't think about anything else if the pain is great. So, man, we are these creatures whose brains can soar to the edge of the cosmos, but you fiddle with us physically and you break a little something, or you imbalance in the chemical makeup, and that's it. We fall apart. We are just these bags of particles. How amazing that when they're doing the right thing, we can engage with the world in such deeply interesting and profound ways. Okay, what else do we have to talk about here? Philip asks, if time is not fundamental, where is the point that it emerges from more basic principles? And how can the universe evolve from a fundamentally timeless basis? And I wish I had something good to say on that, but let me just give a couple of quick thoughts. We are familiar with qualities of the world that you might have thought to be fundamental, but they're not. Refined investigation and knowledge shows us that these qualities of the world emerge from more fundamental starting points. And the example that I like to give, it's very intuitive, is temperature. There was a time when you might have thought in the history of our understanding, we here is now the entire species. There's a time when we would have thought that hot and cold are these fundamental qualities of the world. But then physicists, chemists dig deeper and they realize, oh, temperature, that's nothing but a measure of the average kinetic energy of the particles that make up a substance, whether that be the environment, the air, or that be, a pan that we're holding, right? And if the molecules are moving very quickly in the handle of that pan and you grab it, you scald and you burn your flesh hot. If, on the other hand, the molecules are moving much more slowly, you grab it and it feels comfortable. So temperature, hot and cold, is now recognized to emerge from a more fundamental idea, the motions of the particles that make up a substance. Could it be, as people have kicked around and as Philip is asking, that time is also emergent? Could it be that there are more fundamental qualities of the world? I don't know what to call them. Molecules of time, atoms of time. People use this language, but really making that precise is difficult. But imagine that there are these particles that only when they arrange themselves in a particular configuration, not moving quickly or slowly, that's temperature, but rather arranging themselves in the right pattern, when they do that, a concept of time emerges. Just like when the particles are in the arrangement of moving quickly, the concept of hot emerges. Could that be it? And could it be, therefore, that when the particles of time are not arranged in that configuration, time as we know it doesn't exist? So to answer your question, Philip, imagine a universe. Hard to do because our language is so temporal from the get-go. It's difficult for me to even talk about things without time slipping in. But imagine a time, there it is, long ago, another reference to time, when the universe was in a configuration in which those particles were not arranged in a manner that yields the conventional notion of time. And then at some moment, a temporal notion has slipped in again. At some moment, the particles do arrange in the manner that yields conventional notions of time. And then the universe progresses from there. Now, I don't have the language to even talk about the era prior to the particles arranging in a manner that yields time. But intuitively, I think you can grasp the idea that there could have been a realm where time had not yet emerged. And only when the particles coalesced in the right way, that sounds like a temporal process. There you go, I'm slipping in again. But somehow when the particles coalesce in the right way, time emerges. So you see, the challenge is to develop a completely different vocabulary and a completely different mathematical structure that allows us to talk about processes without time creeping in. And people have worked on this. People have worked on versions of physics where there isn't time and space from the outset, rather there's the relationships between the ingredients. I've never been completely convinced that those approaches have achieved what they seek to achieve, but it's just to say that people do try to develop the language and the math to make more precise the answer that I just gave. But I hope that gives you some feel for how time could be emergent and how the universe itself could have an era in which time as we know it did not exist. So Rajdeep Dar asks, linear or cyclic cosmology? And I would say I veer strongly toward linear cosmology right now. I have been struck over decades, as have many of my colleagues, by the successes of the inflationary theory. I am not saying, as I noted in the episode, I think it again was episode 30, I'm not saying that inflation has been proven. I am saying that it's a very compelling framework for dealing with a great number of cosmological issues and giving rise to a very economical, compact description of how the universe got to be the way it currently is. Now, there are critics of the inflationary theory, including one of the gentlemen who was responsible for the theory itself, Paul Steinhardt. And again, as I emphasized in the earlier episode, I think it's spectacular that Paul, who developed the theory is willing to take a sledgehammer to it to try to break it down and suggest an alternative possibility. It doesn't mean that he's right. It does mean that there's a vibrant conversation that would not otherwise be happening if Paul and his colleagues were not developing these alternate ideas. In the end of the day, it's got to be observation and experiment, mathematical consistency, the predictions that emerge from a theory that determines whether it's the linear version of inflation or Paul's suggestion, as others have worked on too, a cyclic cosmology, a bouncing cosmology. So we will see. I would think that in the next 5-10 years, we will have enough new mathematical insight and enough new data that will be able to answer your question more forcefully. But at the moment, there are these competing proposals. I think the vast majority of cosmologists are in the linear camp, but that could change over time. Okay, let's see what else. Let's see. Okay, that's interesting. So I get Inspector Levin says, I am the original Ludwig van Beethoven. I don't think original in the sense of the original, but probably original in this account. And there have been copycats. Wow. And then he's been put out. Oh, wow. I don't know. All sorts of political intrigue happening on the live chat. So I have not much to say about that, but hopefully everybody's having a good time. That's all that really matters. All right, on to other questions. Easy Sparky, does the future already exist right now? Certainly in Einstein's special relativity, if you allow me to answer this from the perspective back in the early part of the 20th century, back then, I think Einstein would have had a certain degree of warmth and sympathy and agreement in that view that the future already exists. Wow, I should not have chosen this bottle. I just got water all over my face. Just excuse me 1 second as I wipe. Man, I'm gonna need a better cup out here. Anyway, I was trying not to use a plastic bottle. But, you know, Einstein's view is that the whole notion of now, right? The whole notion of what's happening at a given moment in time is highly in the eye of the person, the observer, the beholder. Because if you and I are moving relative to each other, we have different clocks ticking off at different rates. We have different notions of simultaneity. In that episode, I don't remember what it was a while back now, but there was a your daily equation on the relativity of simultaneity, where if you watch that, or if you go back to it, if you're interested, I established that in the special theory of relativity, we learned that things that I say happen at one moment in time, if you're moving with respect to me, you will not agree that those events happen at the same moment in time, right? We're like right now, I would say I snapped my fingers simultaneously at the same moment. But if you were moving relative to me in one or another direction, and you observe those snaps, from your perspective, you would say what happened was snap, snap. Or if you're moving the other way, you'll say what happened is snap, snap. So the notion of simultaneity, what's in the present, depends upon your state of motion. And that's exciting and interesting in its own right. But one implication is that you and I, if we don't agree on the now, we don't agree on the past, and therefore we also don't agree in the future, right? The person moving by would have said, that happened first, and then in the future, this happened. The person moving the other direction would say, this happened first, and then this happened in the future, while I say they happened at the same moment. So observers in relative motion mix up their conceptions of past, present, and future. And therefore, the things that I consider to take place in my future, that's a real notion. I have an unassailable conception of the past. I have an unassailable conception of the future, but it's my future and my past. And things that are in my future can be in your present or can be in your past, depending on how you're moving relative to me. And if my future can be in your past, then in a sense, my future's already taken place. Now, when you look at this really closely, many of the things that then come to mind are not possible. It's not like you can learn about my future before I know about it and tell me about it. No, can't happen. None of those games can be played because it takes time for you to learn about what happened in my future, even if it's in your past. It takes time for the signal to reach you, right? When I look out at the distant stars, I'm seeing the past. It took a long time for that light to travel to my eyes. So I'm seeing something a long time ago, but by the time I am aware of it, it's long past, it's long gone. And therefore, none of the funny things that might come to mind in terms of spoiling causality are possible. But in an abstract sense, is the future already in existence? Yeah. According to special relativity, it is. Quantum mechanics, general relativity, interesting nuances, complications. If you're interested, ask about it. I'm happy to go down. But this, according to that way of thinking about special relativity, the future in some sense is already real. So let's see. I'm going to take a risk and try to drink some more, particularly thirsty today. What do we got here? Well, so Divyam Singhal asks, I just wanted to ask what's your viewpoint on M theory and its progress since 1995. How does it explain dark energy? And look, my view is this. I've said this before. I'm happy to say it again. I am thrilled in the rate of progress in string theory, M theory, in certain kinds of questions. I mentioned one before, that insight into the fabric of space-time may be stitched by the threads of quantum entanglement. That ultimately relies on insights from string theory. That's great. Some of the insights into black holes that string theory has yielded, spectacular. Some of the insights into pure mathematics that have come from string theory. My own contribution, I'm happy to have participated in it. Mirror symmetry and topology change, these are exciting developments. What we have not done is make contact with observation and experiment in the manner that we hoped would happen by today. So anybody who's a research scientist that's listening to this, anyone who's a graduate student who's in the middle of their dissertation, their research program will know you can't predict how long it's going to take. You can't predict what area of science is going to develop rapidly and what area of science is going to develop at a snail's pace. If you interviewed me as a graduate student back in the 1980s, I would have thought that by today, we would have made contact with the supersymmetric particles that string theory requires, or that we would have seen some exotic process that would give indirect evidence for string theory. That has not happened. But again, if you asked me back in the 1980s, will we be able to talk about what makes up the threads of the space-time fabric? Or will we be able to truly understand the entropy count for black holes? I would have said, I don't think so. It's going to take longer. And yet we've gotten headway, made progress in these areas. So on balance, it's exactly what you'd expect. The rate of progress of science is unpredictable. As long as it is making progress in some areas, that means that theory is alive, well, and healthy. And I think that's the best that I can do in describing the state of play in string theory. Okay. All right, what have we got here? I think I may switch over to YouTube for a second, as there were some that I remember over there liking a lot. All right, so one technical question I think it's worth spending 10 seconds on, from Martin Topinka. Why do people use the V of phi plot with a rolling ball in the direction of the gradient of the potential and not phi of t plot to describe inflation? And so what Martin is referring to is, my iPad's on the blink right now, so I can't draw it for you. But you remember, I mentioned before already, I drew this curve that was the plot of V as a function of phi, or maybe this is the direction I drew it. That's probably how I drew it. And imagine that the phi value is like a ball. That's metaphor, but it's a ball in the sense that its value changes over time and rolls down the hill. And the reason why we typically write phi of t instead of v of phi, we could do phi of t. You're absolutely right. Phi starts at a certain value. It stays constant at that value over a stretch of time, and then it drops down. The reason why we frame it in terms of v of phi is what we choose and put into the model. That's the user chosen quality of that model of cosmology. We then use v of phi to write down the equations that determine how phi changes in time. So phi of t for us is generally a derived quantity, whereas v of phi is a quantity that we put in by hand. So we tend to define the model by the things that we put into it, and then we extract from it through calculation certain qualities. And that's why we write down the thing that we pick by hand, and then we figure out phi of t. We determine it by solving the equations of motion. So that's but you're right, you can do it either way. Doesn't matter. Okay, so Van Ron says, Dr. Greene, huge fan of your work. Thank you, Van Ron. Can you recommend a great book on the history of quantum mechanics? Yeah. A great book on the history of quantum mechanics. I do know some. I'm having trouble bringing them into mind directly right now. It's on the tip of my tongue. That's why I'm struggling to. There's a book called Quantum, and there's one word after it. Quantum ages, quantum. If hopefully it'll come to me. But there are a lot of really good books on the subject. I understand you're asking for the history as opposed to the actual subject. I'm going to have to come back to it. Hopefully it will come to me, or maybe even I'll put it in the comments if it comes to me later. Okay, so, what have we got? So Abai Chaco asks, does a particle without mass, could it be motionless? And the answer to that is no. It's a strange idea. If a particle doesn't have any mass, it cannot sit still. I successfully took a sip of water. Wow, congratulate me. Don't have water on my face on that one. A particle that has zero mass is a particle that will always and forever be traveling at the speed of light. So the photon, of course, is the prototypical example. And the photon, I hope I said photon, not proton. The photon, the particle of light, is always traveling at light speed. It's never not traveling at light speed. And there are a lot of intuitive ways you can think about it. As a particle gets ever lighter, obviously, the wispiest of force will give it the largest of accelerations, right? F equals ma. Fix a small value of f, let m go smaller and smaller. The acceleration is f over m. As m goes to 0, the acceleration goes infinite. Infinity goes to infinity, and therefore the particle accelerates arbitrarily quickly. More specifically, when you really look at Einstein's special theory of relativity, it is the trajectories of massless particles that define the causal structure of the universe. They're the ones that set the limit on how quickly a signal can travel from one point in the universe to another. And therefore, they delineate what influences any given process can exert on other events. And so the speed of light is an interesting concept because we name it the speed of light because it is the speed of light, but it's more than that. The special theory of relativity is not so much about the speed of light per se as it is about the causal connections, the events that can influence each other by any kind of signal sent with any kind of particle, light being one particle, but gravitons, massless particles that we believe exist, would also be traveling at the speed of light, or call it the speed of gravity, as would any massless particle. They all fall into the same category of particles that cannot be motionless, always traveling at one and the same fixed speed. Okay. What else have we got here? Albion asks, I've read once there's a mathematical relationship between dividing by zero and black holes. Is it true? Well, sort of, not really. I mean, not in any deep sense. When you look at the solution to Einstein's equations in the general theory of relativity, and you look at the amount of curvature at the origin, at the 0 point, say, of your coordinate system for a black hole, you find that the curvature explodes. It gets arbitrarily big. And depending on the exact solution you're looking at, it goes like a power of your distance from the origin. So imagine it's the 6th power, that the curvature goes like 1 over r to the 6th power for the black hole solution. Then as r goes to 0, 1 over 0 to the 6 is 0. So it's like dividing 1 by 0. So the curvature at the origin of a black hole is like dividing by 0. But that's the nature of a certain kind of curvature singularity that need not be associated with a black hole. It could be associated with, any solution. Now, some would say, aren't singularities always cloaked with a black hole horizon? And if that's the association you have in mind, that's fine. That's true. But I guess why my gut reaction to say yes and no is there is some quip. I don't know if it was Stephen Wright or a comedian, or maybe it was Einstein or somebody like that. I don't know. Don't quote me on this quote. But somebody said black holes are the result of God dividing by 0. And when I hear it framed in that way, as you no doubt can tell by the look on my face, it's funny, clever perhaps, but there's nothing more than that to the statement. So I think my interpretation of the curvature going to infinity at the origin of the coordinate grid for black hole solution is probably the best real connection between divided by 0 and black holes that you can get. So DM asks, and is very excited about this question, so exclamation points, says, even though things can perceive the same event at a different time, isn't there an absolute time that an event happened? And the answer to that is no. Your intuition says that, DM, exclamation point, question mark. But your intuition is something that we've learned from Einstein is generally a poor guide to understanding the true nature of reality. So really what Einstein taught us is that there's no universal notion of time. So an event can take place, and you may use a notion of simultaneity to determine when that event happens. What do I mean? The firecracker goes off, and you look at your watch, and you're like, okay, it went off at 12 noon. And you're saying that those two events are simultaneous. That's what it means to say that an event happened at 12 noon. You mean the event happened and my watch struck 12. Simultaneous events, that's what I mean by the event took place at 12 noon. But as I described before, different observers moving relative to you will not say that those two events were simultaneous. They will say either that your clock struck noon before the firecracker exploded, or they will say that the firecracker exploded and then your clock struck 12 noon. And so the conception of when an event took place depends upon who is doing the observing, who's doing the measuring, the clocks and the state of motion that they are undergoing. Why does that matter? Why does that matter? Why does it matter? Because it radically changes our perspective of the world. Our view of the world, according to Isaac Newton, was there's this universal clock ticking out there in some metaphorical, abstract way, and the events of the universe simply unfold as that clock ticks off time forward. And because the clock is universal, you and I and everybody else will agree on when events take place. And what Einstein did is he took a sledgehammer and he smashed that universal Newtonian clock, and the shards that shot through space are the individual clocks that each and every observer carries with themselves. And so time now is not universal. Time is in the eye of the observer, a completely different perspective on how the world works. I mean, don't you find it mind-blowing that if you and I, imagine you and I are on opposite ends of the universe, billions of light years apart. And let's say initially we're not moving relative to each other, which means we will agree on what things happen at the same moment. But then if I get up and I start to walk toward you or away from you, my conception of what happens right now may swing hundreds of years into your past or hundreds of years into your future. Things that you would say have not yet occurred. I would say, are you kidding me? They already occurred. Things that you would say are long past, I'd say, no, they just happen right now. That's crazy sounding, but it's true. That's why it matters. That's what Einstein's relativity of simultaneity gives us. Okay. Chetan asks, is it true that photons do not experience time? And this question comes up now and then, and I ask you to think about your question a little bit. So you say, photons do not experience time. Normally, I don't need to parse a question carefully, but this one I do, because what does it mean for a photon to experience something? We anthropomorphize the particles of the world, and we imagine that they kind of have some experience of time like we do, some conception of time passing. And that's not true, I don't think. I don't think photons have any conscious awareness. So the question of time passing for them is a very different proposition from the notion of time passing for us. And therefore, I always find it a little uncomfortable to answer this question as if it were the case that a photon is consciously aware. Now, why do I say that? I say that because, yes, poetically speaking, there is a sense in which if a photon did have conscious awareness, it couldn't experience the passage of time in a sense that its clock would be dead fixed at one moment relative to our clock. Or said differently, from its perspective, it would see time on our clock elapse infinitely quickly. All events would happen at the same moment. So the notion of the photon being able to see the world as we like to see it, events happen one after another with some finite separation in time between the events, that would not be the photon's experience. But I urge you to take this with a grain of salt, because photons don't have that experience whatsoever. And therefore, if it excites you and you find it interesting to think about how the world looks from the perspective of a photon, be my guest. It's fun to play those games, but don't take it too seriously, because no conscious awareness is ever going to have the perspective of a photon. Okay, what do we got going on here? Yeah, so Garden asks again, so what would a photon see in its one moment? Again, I'd say the same caveat. I don't even know what it means for a photon to see. Has it see with another photon? Another photon brings the image of light to the eyeball of the photon. So you see, we get into a muddle very quickly. Putting all that to the side, which I shouldn't do, but just because you ask, and that's an unsatisfying kind of answer. In some sense, the photon would see all of space in the direction that it's moving, infinitely compressed, right? Because it's going at the speed of light, which means the gamma factor would be infinite. So distances that it looks at, whatever the heck that means, would be infinitely compressed. And moreover, because its clock is ticking off infinitely slow compared to the clocks that it's moving by, it would see those clocks ticking off, at a rate of time that would be very strange, So it's hard to really answer this question. As we can talk about our view of the photon. Our view of the photon is that if it were carrying a watch, that watch would be ticking infinitely slowly. You can say that, but the real way to answer that question is, don't talk about photons. Talk about a particle traveling at 99.999999999999999% the speed of light. That's pretty darn close to the speed of light, but not exactly equal to the speed of light. And that small difference is kind of vital, because that is a perspective that, in principle, a particle or even a human being can be within. I mean, if a particle is traveling at that speed in the opposite direction from its perspective, whatever that means, I am traveling this way at that high fraction of the speed of light. And again, we know what happens in those circumstances. I look at your watch, see it going slow. You look at my watch, I see it going slow. So those are the things that, if I look at an object moving by me, I see it compressed in the direction of motion, so that if an object is moving by me at incredibly high speed, close to the speed of light, it will be like a pancake, twisted pancake, as it turns out. So these are the things that we can say, but really thinking about the perspective of a photon always is going to get you into trouble. Niels Bohr was famously fond of saying that if you ask a question that refers to a quality of the world that it is impossible, fundamentally impossible for you to ever access, then you're likely to find that your attempt to understand it is going to hit a brick wall. And that's this perspective of a photon. You can talk about it, you can poetically think about it, but you can't ever access it. And therefore, when you head down that trajectory, it's a dangerous one to take seriously. Aryan Tiwari asks, hey, Prof, love the quantum series. What is nothingness? The probability of you seeing this is 1 in 522. 1 in 526 right now, apparently. So look at that. You've won the lottery. I'm sure you'd rather have won the real lottery over this one. But so what is nothingness? Subtle question. You wouldn't think so. Nothingness is the absence of stuff. Stop, right? We should just stop right there. But the problem is you have to carefully delineate which stuff you are imagining being absent. Sure, if you imagine that material objects, like my contact lens box and, my water bottle, if all of that kind of stuff was gone, you'd have a certain kind of nothingness. You'd have emptiness, empty space, but space would still be there. Time would still be there. And if you look really closely in the quantum description, even the fluctuations of the fundamental fields would be there. The electric field, magnetic field, all bubbling around in the quantum vacuum. So that doesn't all of a sudden seem like nothingness at all. That seems like a whole lot of something. It's just not the usual some things from everyday experience. So then you want to go further and say, can I really imagine a nothing that doesn't even have any space, no time, a true nothing? And you can imagine that. And it's something that in principle you can write down a mathematical formalism that would make use of. It's a spatial manifold, if you will, where the size of the manifold has shrunk all the way to zero. So the space-time itself has gone away. It's not that it's shrunken within a environment, which is itself got the qualities of space and time. We're actually imagining all of space-time itself. The cosmological solutions where you wind the film back, those guys are getting smaller and smaller, not in an existing realm, but the realm itself is disappearing. So you can approach the ideas of nothingness, but it is a surprisingly subtle and curious idea. If you want to have a full look at it, we have from time to time, I do this just because I think it's interesting for you to look at things. There is a World Science Festival program called What is Nothingness, or What is Nothing, or The Meaning of Nothing, or something like that. And it is the parsing of the conception of nothing from various distinct points of view. And it's interesting to see how different ways of approaching that question yield different answers. Amanda asks, can you elaborate on the different types of infinities? Yes. I should do a whole episode on your daily equation on the different kinds of infinities. The two that are most prominent and easy to understand are the infinity that we all used when we were kids, 1, 2, 3, 4, 5, the various incarnations of that you say something against, and they say, well, I twice on you, 3 times 4, you have this bickering going on, and only some kid is always going to jump to infinity to try to win the argument. And that's one type of infinity, just counting the natural numbers, 1, 2, 3, 4, 5, up to infinity. But you can ask yourself, how does that infinity compare to the infinity that also allows decimals and fractions? 0.124139759 and so on, or pi. That's a decimal, 3.1415925 goes on. I can't go any further than that. Many of you can beat me in that, no doubt. So the infinity of the counting numbers versus the infinities of the decimal numbers is an interesting question to ask yourself. And you can prove that the infinity associated with the counting numbers is a smaller infinity. A small infinity, that's like a weird idea. You'd say, well, infinity is infinity, right? But you can ask yourself, can you partner up all of the counting numbers with all of the decimal numbers? So you say, let me call 1 the number 0.0126. Let me call 2 0.0129, and so on. You try to pair them up, and you can prove that you will run out of the counting numbers. And when you try to marry them in that pairwise fashion, there'll be leftover decimals that don't have a whole number partner in that kind of attempted pairing. And the beautiful argument that comes from Cantor's diagonal argument, and I'll do that in an episode at some point, maybe, if I find the time to do it. I would love to do that. But you should look that up, because it's a very simple argument and kind of mind-blowing. Cantor tries to line up the whole numbers in the manner that I just said with the decimals, and he's able to prove the existence of a decimal that will not be partnered with a whole number, and therefore that the decimals have a larger cardinality, a larger infinity than the counting numbers. And there are various games further that you can play with this and get various levels of infinity. Very curious, very puzzling idea, but one that is very powerful and very interesting. All right, so what else do we have going on here? Yes, thank you. Brian DeGraw, was the book Quantum Generations? It was Quantum Generations. That's exactly the book that I had in mind. I haven't looked at it in a long time, but I remember thinking that it did a very nice job on the history of quantum mechanics. So we just crowdsourced the answer. I used up one of my lifelines to get Brian DeGraw to chime in with the correct answer to the question about a good book on the history of quantum mechanics. So thank you. Steve Baggins, hello, greetings from Greece. Can you explain the function of the Z boson? And sure. When people were trying to understand the basic forces of nature, obviously we knew about gravity for a long, long time. We knew about electricity and magnetism for a long time. Maxwell and Faraday and others gave us a deeper description of electricity and magnetism that blended them into a unified whole called the electromagnetic force. And in the early part, well, the middle part of the 20th century, people began to go further to describe the nuclear forces, not gravity, not electricity, not magnetism, but the nuclear forces at work inside the nuclei of atoms for the most part. And there is a force called the weak nuclear force that was discovered experimentally and understood theoretically in a handful of papers, but ultimately the ones that won the Nobel Prize. It's the paper of Sheldon Glashow from 61, and the paper in 66, 67 by Abdus Salam, and another paper by Steven Weinberg. And in this so-called electroweak theory, we recognize that the weak nuclear force is transmitted not by one particle, the way the electromagnetic force is. So the electromagnetic force, light, is communicated by photons, one type of particle. The weak nuclear force is transmitted by 3 types of particles. And those particles are called the W plus, the W minus, and the Z0, the Z boson. So what is the Z boson? The Z boson is one of the 3 particles that transmits the weak nuclear force. It is the only particle of the three that doesn't carry any electric charge. So whereas the W plus charge, W minus negative charge, they carry the weak force, and also they have electric charge. So the electromagnetic force is right in there blended with them. The Z is the weak nuclear force carrier that does not also carry the electromagnetic force. The electric charge of it is zero. Thanks for that question from Greece. So Mohit asks, if we assume that the guiding wave is real for a quantum particle, is it possible to not get the interference pattern when we don't see a flash? Shouldn't the photon and electron be interacting somehow? I understand the first half of the question. I'm not fully appreciating the second half, so I'll take a stab at it. There's an episode in your daily equation. It is the mystery episode, episode 24. In episode 24, I discussed the approach to quantum mechanics called the de Broglie-Bohm theory. And at the very end of that episode, I was rushing and I made one little mistake in an equation I wrote down. None of you caught it, but I was so uncomfortable with this little mistake. I probably should have left it, that I took the episode down and I was going to redo it or fix it, and I haven't gotten around to doing it. But this question is associated with that theory, because in that theory, in the de Broglie-Bohm theory, it's not as in traditional quantum mechanics where we say you've got a particle or you have a wave, right? And you have both of those blended in some strange manner. But when you observe the entity using equipment that's sensitive to its particle qualities, you only see the particle aspect of the wave and the particle aspect of the entity, I should say. And when you're using equipment that's sensitive to the wave-like qualities of the entity, then you only see the wave-like qualities. In the de Broglie-Bohm theory, that's not the case. It's not particle or wave, it's particle and wave, because the wave function in quantum mechanics, the probability wave in quantum mechanics, in the de Broglie-Bohm theory, it's a real thing. It is the guiding wave in the language that Mohit is using. So you've got particles moving around, and you've got these quantum waves, and the quantum waves simply push the particle around. And they push the particle around in an unusual manner, a manner that the theory postulates. And the manner that it pushes the particle around can yield and does yield the interference patterns of quantum double slit experiment. So the double slit experiment in this approach is not described in the usual way of the wave for the particle goes through the two slits, it overlaps, yields an interference pattern, and then when the wave hits the screen, it turns into a particle because it's being detected by a detector that's sensitive to particles. And that forces the wave-like nature to go away and the particle-like nature to appear as a dot on the screen. And that gives you the interference pattern. In the de Broglie-Bohm theory, you've got particles going right from the gun through the openings and hitting the detector screen, and they are particles through and through the entire journey. In fact, you can plot their entire trajectory. It's not as though when you think about them as particles going through one slit or another, the interference pattern disappears as it traditionally does in the usual story. Rather, the wave, the quantum wave also, in addition to the particle goes through the two slits, it interferes with itself, giving the overlapping interference pattern. And that particular wave configuration pushes the particles to accumulate where the wave is big and not to accumulate where the wave is small. And that gives you the band-like structure on the interference screen. So it's a cooler, well, not a cooler, it's a more understandable explanation of the double slit experiment. It's less mysterious than the usual explanation. It allows particles to have positions and speeds. It just augments the influences under which the particles are subject. The influence of this new guiding wave comes into the story. So you might say, well, why don't people talk about this theory? That's an interesting sociological question. I think the only physics part of it is this theory is manifestly non-local, right? Quantum entanglement has a non-local quality already, but it's kind of hidden. It's not in the mathematical formalism that you start with. It kind of emerges later on that there can be these states that have these long-range correlations. But the fundamental Schrodinger equation that you start with doesn't have any non-locality in it. In the de Broglie-Bohm theory, the fundamental equation does have non-locality in it from the get-go. So the non-locality is more in your face, and that has troubled many people. I don't really know why at some deep level, because if the theory has non-locality in it, who cares whether it's like in your face from the get-go or emerges downstream when you recognize that certain states exhibit non-local correlations. Be that as it may, the de Broglie-Bohm theory is hardly spoken of, even though it allows you to still talk about particle trajectories and particle speeds and positions. Wow. Quantum mechanics in which particles have positions and speeds. Easier in some sense to grok, to understand, to wrap your mind around, and yet it has not caught on and is not something that people, for the most part, take seriously. Although there are some wonderful researchers around the world who are developing the subject further and have been for decades. And who knows how it will all play out. Maybe physics classes 100 years from now will be focusing upon the Bohm-de Broglie theory, because that one has been developed and that one wins out. And I should say the Bohm-de Broglie theory doesn't have a quantum measurement problem. When you measure a particle and you find it here, it was here and is here. It's not as though it was in all these other places and then it materialized there responding to your observation. No, you don't need weirdness like that in the de Broglie-Bohm theory. What you measure is what was there, just like in the old Newtonian point of view. So you might say, wow, it's a return to normalcy. However, because of that non-locality and also the difficulty in making it a fully relativistic theory and the difficulty of making a quantum field theoretic version of it, yeah, I'm being a little bit quick when I don't list all of the problems that the theory has, but those challenges have kept it from gaining momentum in terms of the level of acceptance that people have of it as a viable approach to quantum mechanics. Anyway, I hope I answered Mohit's question. That was my best interpretation of what Mohit was asking. Professor Greene asks, my zombie lick? Huh, not gonna parse that name. Professor Greene, what new technology or physics development do you expect or hope to be released in the next 10 to 20 years? I don't know. I'm not a futurist in that sense. I don't really follow the technological trends. But if you asked me, where do I see spectacular rate of progress? How can it not be in AI, artificial intelligence, and general artificial intelligence? I mean, I had a conversation just before this whole pandemic thing hit. I was in London. I had a conversation with Demis Hassabis, one of the folks who really has revolutionized the subject. And it was just amazingly exciting to hear about the things that they're doing, the possibilities of really, for instance, making progress on deep physics problems by having a system that can learn the patterns of reality by looking at the data and probably looking at earlier attempts to articulate the patterns in the data mathematically, and then perhaps to be able to go further and suggest deeper insights that, as of today, we have not yet ourselves made. Wow, it's like an artificial physicist. That's exciting, and the whole field of consciousness studies, I think, can radically change if we get to a point of artificially intelligent beings that seem to really have qualities that we have long thought to require a human brain. I think these things are deeply exciting, and were I just starting out in science right now, I'd be quite tempted to work in these areas, because it's not that physics has reached the dead end. Everything that we're talking about is hugely exciting, but it's nice to be at the beginning. We're not at the beginning. Well, maybe that's hubris. I was going to say we're not at the beginning of physics. Maybe we are. But I would say that, we've been at it. Let me put it this way. There's a corpus, there's a literature in physics that goes way back. I don't know where you want to begin, but let's say there's on the order of 350 years of literature in physics. There isn't that kind of long literature for artificial intelligence. So it's exciting to be at the early stages, to write the early papers that really set the agenda for the subject going forward. So that's my best answer, I think, to the question of exciting developments in the next 10 to 20 years. Nave Ball asks, can Schrodinger's cat experiment be a proof of parallel universes? Well, David Deutsch certainly would say so. David Deutsch, I think many of you may know, as a deeply insightful physicist, philosopher, written some spectacularly interesting books that I highly recommend. I don't remember all titles, but I think one was called The Fabric of Reality. I remember that one because my own book, Fabric of the Cosmos, has kind of a similar title, so people sometimes mix those up. I think he has another book that I've not yet read. I thumbed through, that is something like The Start of Infinity or The Beginning of Infinity. I don't recall. But in The Fabric of Reality, David Deutsch argues that the kinds of quantum interference processes, the superposition that allows objects to occupy distinct quantum states simultaneously, he argues that that really is proof of parallel universes, that the many worlds interpretation of quantum mechanics is the only way that picture of the world makes any sense. I was not convinced by his argument. I found it interesting, but I don't by any means think that there's anything that we currently have in quantum mechanics that nails down the many worlds approach as the only way of thinking about quantum reality. Some of my colleagues don't agree with me. Sean Carroll, some of you look at his stuff. He's great. His new book, Something Deeply Hidden. He argues in there forcefully for the many worlds approach. And these are arguments that are worth taking seriously, but it would be premature by a long shot to say that we have reached consensus that the many worlds approach is the right approach to quantum mechanics. There are many people, perhaps they write less and are less publicly visible, who are very adept at giving reasons why the many worlds approach is yet to be established, either mathematically or observationally. So again, like multiple universes, not in the quantum sense, but say in the inflationary cosmology sense, good to have these ideas at your disposal, good to think about them, but it's going to take much more than we currently have to establish that they are correct. Okay, what have we got going forward here? By the way, what time is it? Oh, it's 4:45. Ooh, sorry, I'm starting to lose my voice. Let's see what we have. Somebody who have not asked a question before. Joel Jarvinen, hello from Sweden. Hello, Joel in Sweden. I spent a lot of fun time in Sweden. I used to go there. I used to go to Gothenburg. I used to go to Gothenburg basically every Christmas and every summer. I would spend 2 to 3 months in Sweden every year when I was younger. I loved the time that I spent there. Once went up to the Lofoten Islands. I know that I'm getting the name pronunciation wrong, in Norway. That was a great time. But anyway, enough of that. To the question. Thank you for the inspiration through my theoretical physics master studies. My pleasure. I'm curious, do you think that there is an objective reality? Similar to a question we asked earlier, Kant did, but I don't because how would you prove it? Well, yeah, so this is a different take on the earlier question that we addressed. And look, it's absolutely the case that we only have access to the purported objective reality through subjective experience, right? I mean, I look around the world and I imagine that I'm seeing objective entities that are really there, the ceiling, my laptop, this display, my bottle of water. But in reality, you and I both know that this bottle of water, or this yellow, right? What is this yellow? Is this yellow here? No, no, it's deeply in here, right? There are the photons entering my eye, tickling my retina, sending a signal into my brain. And my brain, because of its evolutionary development, has become adept at deciphering the signal that my eye is receiving and saying, yellow. It even projects it out into the world. I don't see the yellow in my brain. I see the yellow out there, even though all of this crackling, this cascading of particles is happening inside my head. So all I have access to is the crackling of those particles. And in fact, I don't even have access to that. I can't see the particles coursing through my brain. I'm only able to access the aftermath of those processes. How I do that, I don't know. Neither do you, neither does anybody. How is it that I have this inner experience? How is it that I have this world inside my head that evolution has led me to believe is out there, even though my experience is just inside? So I agree. You can't ever prove anything about the objectiveness of those kinds of subjective experiences. However, there comes a point as a physicist where you put those possibilities, you say there's a real possibility that it's all inside my head. I mean, I'm going to put it to the side and I'm going to imagine that there is an objective world and I'm going to do all that I can to try to explain it mathematically. And that's what you do. So it's a very pragmatic perspective. My language in my books and my language here speaks as though there is this objective world. My attitude is that I am working on physics to explain that objective world. But you're right in that I only have subjective capacities to engage with whatever that objective world is, even if it doesn't exist. So you're right. We find ourselves in an interesting conundrum. But from a flat-footed physics perspective, I allow for that possibility. I chunk it over here, and then I say, it is useful. It is useful for me to imagine that there is an objective world. It's useful for me to imagine that my investigations are trying to find the patterns in that objective world. And then I simply admit the fact that my only means of accessing that objective world is through subjective experience. And I leave it at that, just because there's not much more I can do with that observation besides marveling at it and then going forward. So feel free to answer back on that if that didn't address it enough. I'm happy to go further if there's anything more specific that you can guide me toward. Yatish Argawal. Hello, Dr. Greene. Love the way you explain physics. Thank you, Yatish. The strings in string theory are said to be made of pure energy. So what is that energy? Is it tangible? Yes, right. So tough question. And, as I've described earlier, even explaining what energy is in any fundamental sense is a challenge. You go to a Physics 1 textbook, and the Physics 1 textbook says usually energy is the ability to do work. It's the ability to move something through a distance, right? It's with energy that we're able to cause those processes to take place. But that's not really telling you what energy is. It's telling you sort of what energy does. If you're asking like, I just want to know what it is, what is it made of something? Does it originate from something more fundamental? I mean, these are tough questions. But the way that I like to think about it is this. Even though I don't really know what energy is, I know that the universe has it. I know that the universe is able to have particles and objects move through distances. So the universe has some energy. And then, if string theory is correct, I would say that the strings in string theory are the most fundamental carriers of the energy of the universe. Again, regardless of what that energy is, where it comes from, I can't answer questions like that, unfortunately. But if string theory is correct, think of the strings as the most fundamental carriers of the energy that the universe has. And how do they carry that energy? They carry it through their motion, through their vibration, through their intrinsic heft, perhaps. And so, in this way, the strings in string theory are the most fundamental currency of the energy budget that the universe has. Okay, what else here? um, Bonnie asks, try a Brita water bottle. Okay, I will try that for next time. Thank you for that suggestion. Okay, what else should we talk about here? Nikita asks, hi from Belarus. Does knowing math behind physics concepts help you to imagine the physics concept? For example, could you imagine the fourth dimension knowing its math, or would you have trouble without knowing the math? And without a doubt, the answer to that question is yes. So the way I go about envisioning things in physics that I understand mathematically, I don't understand everything, of course, but the things that I understand mathematically, I use that math to tell me a parallel story to the visual version that I build up based upon the mathematical understanding. So, for instance, when I'm thinking about the fabric of space ripping, to give one example that I had a good time participating in the discovery years ago, in order to have a mental image of the fabric of space tearing, I have the mathematics right here. I have the mathematics of these three-dimensional spheres shrinking down small size, and I understand what that means in the equations. And then I see this field, a Higgs-like field, changing its expectation value as I go through the singularity classically created by the shrunken three-sphere. And as it does that, the Higgs field blows up these other two-dimensional spheres. I can see all that happening in one part of my brain because I can run the mathematical progression in the other part of my brain. I'm not talking left-right stuff here. I'm just talking about the kinds of things that you have in mind. And so I'm constantly using the mathematical description to inform my visualization. And without that, I'd have a lot of trouble. And I've often said that I wonder how the good science writers, how they do it. Maybe they have enough of the background that they also have a mathematical understanding. But if you don't have a math understanding, I would have a lot of trouble writing about any of these or talking about any of these ideas, because if I had knowledge that was already digested into a non-mathematical form, how would I know if that digested version was leaving out critical things, or if my version of the digested version was now taking it in a direction that made it inaccurate or false? So I always need to go back to first principles, the mathematical understanding, have that as my overarching rubric within which I can develop visualizations or everyday language descriptions, constantly checking it against the math. And if I violate the math, I'm in a position to say, okay, that metaphor, that image, it violates the math, but that's okay. That's not a vital part of the story. I'm willing to bend the rules there. But if I didn't know the math, how would I ever judge whether a metaphor or an image was too far away from the actual description to be worthy of articulating? So the answer, Nikita, is absolutely yes. And to imagine the fourth dimension, well, look, I can imagine the fourth dimension again mathematically. Can I really turn that into pictures? Tough. I can sort of turn it into three-dimensional pictures, but so can anybody. So I'd say that just because you have the math doesn't mean you'll have a visualization. But if you do have the math, it will allow your visualizations to be much more sharply configured. Okay. Um, so what do we got? Um, what is the idea behind quantum computers? That's a good one. And well, there are a lot of ideas behind quantum computers, but I think the question is, what's exactly quantum in a quantum computer? Because you have a computer on your desk right now, or in your pocket. Your phone's a computer, and it relies upon quantum ideas. The building of those integrated circuits required quantum mechanics to be able to move electrons on sufficiently precise trajectories to carry out the processes that we want those particular chips to achieve. So, since quantum mechanics is already part of the story, what is a quantum computer? Well, a quantum computer is one that doesn't just use quantum mechanics in the technology per se. It actually uses quantum mechanics in the calculations. An everyday ordinary computer may have quantum devices within it, but it's carrying out classical computations. We want it to carry out quantum computations because, and here's where the many worlds approach, metaphor or real, I'm not going to commit one way or another, is helpful to think about things. If you're able to do a calculation in many worlds simultaneously, you could break it up. You could have parts of the computation take place in different universes. And if you were then able to extract from those many worlds the answer that you were looking for, you'd have sped up the computation by splitting it up among these different realities. Now, whether or not those many worlds are real, or whether this is just a way of figuratively talking about the mathematical process, doesn't matter for the conclusion that you can draw, which is that certain calculations can be done much more quickly in the quantum realm because of this divide and conquer, if you will, approach. And people are getting to the point where quantum computing is real. And that's hugely exciting. And so we'll see where this takes us. Now, I should say, it's not as though any calculation is amenable to this huge speed up that quantum computation promises. There are some calculations that we know how to break them up, the algorithm necessary for a quantum computer to win by a huge margin over a classical computer. But there are other processes, other calculations that we don't really have an algorithm in order to program a quantum computer to do that calculation and to be assured that the quantum version will be lickety split compared to the classical version. So it's not that you should think that once quantum computers are ubiquitous, that every calculation will be sped up exponentially, but some will. And some important ones will. And who knows, as we go forward, people may become better adept at using the quantum environment to speed up calculations that today we don't know how to speed up. So all hugely exciting, all definitely very exciting. Okay. So I'm going to ask Ariane's question because I know I had one before, but what is a dimension? Also love that beard. Well, so Ariane, you mentioned this, that what beard? I'm cleanly shaven, I think. Maybe it's the lighting or something. I don't know. Or maybe you're talking about my birthmark right over here on the side of my face, which like when I usually do television, I got makeup on to cover, but I'm out here just completely natural, if you will. So Ariane, I'm curious what beard you're talking about. But in any event, what is a dimension is a damn good question. And a dimension is any independent direction, a spatial dimension, let me do first, is any independent direction in which motion is possible. So in our world, we all know that motion is possible in three independent directions. I can go this way, back and forth. I can go left and right, and I can go up and down. Of course, I can also go at an angle, but if you go at an angle, that's just a combination of moving left and right and then moving a little bit back and forth, and then a little up and down. So an angle is not an independent direction. It's a combination of this, and that. Now, when we talk about extra dimensions of space, we really mean that there are new independent directions in which you, in principle, could move that you cannot access by some combination of left, right, back, forth, up, down. That's a curious idea. And that's what string theory demands. A handful of extra directions that, in principle, if you were, say, small enough, you'd be able to move that you simply cannot access through the known 3 dimensions of left, right, back, forth, and up, down. So I've answered your question, Ariane. I'm curious for you to answer my question, but no need if you don't want to. So Quantum Jump says, I hope all our friends from India are well after the cyclone. I've not been following the news. Was there a big cyclone? I'm sorry to hear that. And I agree. Hope everyone's okay. So Uzgur, sorry, how to pronounce it. Will life always in other universes after our universe dies? So I guess the question is, will there always be life in other universes after our universe dies? And look, number one, we don't know if there are other universes. Big part of my answer to this question. But if there are other universes, it depends what kind of multiverse we're talking about. If we're talking about the many worlds of quantum mechanics, then there's something interesting happening, because if that is correct, and there really are these other worlds in which the quantum probabilities sort of branch off and other outcomes of given processes take place, then you can argue pretty convincingly that there's a non-zero probability that life can continue indefinitely. And if there's a non-zero probability for that, it's not as though quantum mechanics has within it a rule that says there's a 0 probability that life will persist beyond a certain time scale. I'm not aware of any such statement within the laws of quantum mechanics. And that being the case, if every possible outcome takes place in some universe, then however improbable the nearly or literally infinite longevity of life might be, there's going to be some realm where that nearly 0 probabilistic outcome is realized. And that would suggest that life could persist arbitrarily far into the future in some other universe. But again, it's funny, I saw somebody mention something that I took solace in that, and I don't really, that's just not true at all. For instance, in my book, Until the End of Time, I spend virtually no time on the multiverse. I was focused, and I am focused in that book, on how to make sense of the finite nature of life and the finite nature of consciousness in this universe. Even though the timescales may be large and seemingly abstract, my focus is trying to make sense of this reality, subjective, objective, however we want to describe it. So it's fun to talk about the possibility of life in other parallel realms. But for the serious questions I was asking in the book Until the End of Time, I don't think there's a whole lot of insight that the multiverse provides. Ariane says, "This is my attempt at a joke." Okay, sorry I didn't get the joke. Apologies. I must be thick, as I don't know what the joke is. But in any event, viewer asks, what is the opposite of entropy, and could that have been in place before the Big Bang? Well, entropy is not something that I've yet really spoken about, which is kind of surprising, because that's where my head has been for a while now. When you're talking about the unfolding of the cosmos over arbitrarily long time scales, the second law of thermodynamics and the relentless increase in entropy is an essential guiding principle. And yet we haven't spoke much about it. So what is entropy? Entropy is a measure, in colloquial terms, of the amount of disorder in a system. But that sounds very subjective. What do I really mean by that? What I mean by that is, take any physical system and ask yourself, how many ways could I rearrange the fundamental ingredients and not have an impact on the macroscopic presentation, the look of that system? And if you have a very ordered system, if you rearrange its ingredients, it becomes disordered, out of order. It will recognize it'll be different, and therefore there are very few rearrangements. And entropy is the count of the number of rearrangements. So if something's very ordered, the count is very small, the entropy is low. In a disordered environment, like the air in this room right now, the particles are rearranging their configuration all the time. And yet, as I look around here, I don't notice a difference. I don't sense a difference. Macroscopically, it has the same properties. And therefore, the air in this room, or your room, has a relatively high entropy because there are a huge number of rearrangements of the molecules of air that leave your environment seemingly unchanged. Entropy is a count of those rearrangements. Entropy, therefore, is high for that circumstance. Now, the question was not only what is entropy, but what's the opposite of entropy? And if you think about entropy as disorder, the opposite is order. And therefore, the question is, could that have been in place before the Big Bang? The answer is yes. I don't know about the before part, but at the Big Bang, our best description of the universe imagines that the Big Bang was highly ordered, very low entropy. And we have been living through the aftermath of that low entropy beginning ever since. Entropy has been rising steadily in some sense since the Big Bang. We are a part way along that trajectory. We are highly ordered beings existing within an environment headed toward ever greater disorder. The fact that we're here relies on the low entropy starting point, because if the universe had a high entropy beginning, it would have been disordered at the beginning and disordered all the way through, and there'd be no opportunity for ordered structures like you and me to form. So the answer is yes. It's called the past hypothesis. The past hypothesis, as its name indicates, hypothesizes, doesn't prove. It hypothesizes that the Big Bang, the earliest moment of our observable universe, had high order, had low entropy, exactly as you, viewer, as your name seems to be, as I see here, have suggested. So, absolutely right. So Christopher says, hello, why do black holes have different masses and sizes when all of them consist of an infinitely dense singularity? Yeah, that's a quite natural question. And I do have some more water under here. So as you watch me pour, I will start my answer, or you probably can't see me pour out of this source here, but you will see the aftermath of that. And yes, you might say, look, if a black hole is nothing but this dense thing in the middle, if that thing in the middle has infinite density, then it would seem like all black holes should be the same. They all have the same infinitely dense core. And number one, we don't know what happens at the core of a black hole. Let's put that out there right now. You often think about the core of a black hole as a position in space where all the stuff that fell in is sort of compacted together. But that's kind of the wrong image. The center of a black hole is more like a moment in time as opposed to a position in space, which is one of the subtleties that have to do with black holes. But the idea is the infinity that you have in mind. That is a misleading number. Infinity in that setting really is one of those singularities, which I said before is the diagnostic that tells us we don't know what's going on. So don't think about the infinitely dense core as defining the black hole. Think about the stuff that fell into the black hole as defining it. Think about the entire mass of the stuff that fell in as defining it. Moreover, if you have a black hole already and more stuff falls in, then that increase in mass makes the event horizon larger. So the more stuff that goes in, the bigger the physical size of the black hole in the sense of the distance to its event horizon, the larger that size becomes. So the history of the black hole is vital to understanding why it looks the way it does. And if you have two black holes where less stuff has fallen into this one and more stuff has fallen into that one, let's say they began the same, less in here and more in this means this will grow, but not as much as this one will have grown. This one will be much bigger than that one. So from far away, we're sensitive to the total mass that's fallen into the black hole. That gives a measure of the total gravitational pull exerted by the black hole, or the total curvature in the space-time environment created by the black hole. But you need to know the history, because the size to the event horizon and the gravitational pull that the black hole exerts on something far away is determined by the total mass that falls in, even if in both cases the masses gets crushed down to a very small size. Okay. Nesma asks, why was bicep 2 proven wrong? Why was bicep 2 proven wrong? You may recall that bicep 2 was this experiment down at the South Pole that reported this very exciting observation of what they believed was the imprint of ripples in the fabric of space coming from the Big Bang itself, primordial gravitational waves leaving an imprint on the cosmic microwave background radiation. That would be hugely exciting. That would be using observational tools to gain fairly direct insight into the Big Bang itself. In fact, as inflationary cosmology, what we did in episode 30, predicts the possibility of these primordial gravitational waves. When Bicep 2 made that announcement, there was great excitement in the inflationary cosmology community. You may recall there was a video of Andre Linde, one of the founding physicists of inflationary cosmology. Someone came to his house with champagne to inform him of this observational result. And so great excitement. What turned out to be the case, however, is that the Bicep 2 team, how to describe it? Some would say they jumped the gun. Some would say that it's just part of scientific progression, whatever. But the excitement that their paper initially generated turned out to be premature, because analysis of the data showed that dust in the Milky Way galaxy can yield the same kind of signature that they may have mistook for primordial gravitational waves. I say may have because the writers of that paper, they argue that they never said that the data proved the existence of primordial gravitational waves. They were just reporting on their observations. Some reading their paper interpreted what they were saying quite differently. So there's been some argument in the community about this, but it's not worth relitigating that issue at all. If you're interested, again, there's a nice World Science Festival program on that with some of the, some of the founding physicists of inflation, together with the Bicep team and so on. So you can take a look at that. But the bottom line answer to the science question is, dust in the Milky Way galaxy affected the signal in a way that mimicked what you would expect from primordial gravitational waves. Dust in the Milky Way, not so interesting. Primordial gravitational waves, hugely interesting. Unfortunately, it turned out that the dust explanation is the right one. That's what happens sometimes. You think that you've got a big discovery, you're so excited, your heart's in the right place, you want to get the information out there, you want people to know about this, maybe even thinking Nobel Prize, it's all very human, understandable. But it turned out that that data was not supporting the idea of primordial gravitational waves. So Narendra asks, what would happen to entangled particles if one of them falls into a black hole? Would the entanglement still hold? And if yes, can there be any interaction possible between them? So, Narendra, you're asking a question that has puzzled people over the past few years in a significant way. If you would have asked that question 20 years ago, say, the answer was pretty clear because in Einstein's theory, classical theory of the general theory of relativity, the edge of a black hole, the event horizon, is not a special location in space. There's no signpost that says black hole, event horizon, do not pass if you want to be able to get out. There's nothing like that. The location in space that we would mathematically recognize as the event horizon of a black hole is an ordinary region of space with no distinguishing characteristics locally. So if you fall over the edge of a black hole, you don't know that you've fallen over an edge. You're just moving through space, just as we're moving through space right now. And because of that, the perspective was that if you have two entangled particles and one goes over the edge of a black hole, they're still entangled. There's nothing that happens at the horizon that would cut the entanglement. It's, after all, it's just empty space. What's changed in recent years is people have thought about this much more carefully and realized that if the entanglement persists across the edge of a black hole, it raises certain puzzles. It raises puzzles for the conservation of information that we believe happens with the radiation that leaks out of a black hole. You wind up requiring entanglement of a different sort that winds up being conflict with the entanglement right across the edge of a black hole. This has led some to suggest the edge of a black hole might actually be special. Quantum mechanically, it may be special. Classically, it's not, but maybe it is quantum mechanically. And some have suggested that maybe the edge of a black hole is a firewall. Nice image, firewall. What does it mean? Well, it would be a quality of space that basically snaps entanglement. If the thread of quantum entanglement is broken at the edge of a black hole, energy, in some sense, is released. That energy would power a firewall. So your question's potent because if entanglement is snapped, then the edge of a black hole is very different from what we would have thought based on Einstein's theory. And people debate this idea of a firewall. There are others who have even more exotic ideas. My friend Samir Mather at Ohio State University has developed over the course of many years now the fuzzball picture of black holes, where black holes are more or less like stars in a somewhat exotic state of vibrating strings, but there is no event horizon, there is no edge in the way that we usually think about it in the classical theory of general relativity. So these are questions, and of course, obviously, entanglement would have different quantities across that because now there's stuff, the fuzzy stuff at the edge of a black hole. So the bottom line is, I'm not sure the answer to your question. Nobody is. It's debated today, but it's an important one for us to ultimately resolve. Okay. What do we got here? Gayatra asks, do I think there's another possible unified theory other than string theory? Absolutely possible. I'm not dogmatic about string theory. String theory could easily be irrelevant. And that hopefully is something that we'll know. I'd love to know the answer to that in my own lifetime, having spent decades working on the theory itself. And only experiment, only observation can tell us that. And if string theory is irrelevant, does that mean the unification program is over? No. We'll continue to think about it. Our descendants, hopefully, will continue to think about it. And other ideas will be put forward. Other unification schemes will be pursued. So I really want to stress that point. I am interested in the truth. I'm not interested in string theory being that truth, in the sense of it blinding me to truths that might not be string theoretic. I just want us to make progress. And if string theory is part of that, great. That would be happy. I've spent my life working on this, as have my colleagues around the world. How cool that the things that we're doing are part of the stepping stone to the deeper understanding. Yes, I'd love that. But if that's not the case, that's cool too. If it's not the case, we can throw string theory away. And in that way, we would have made progress, not by having the right theory, but by discarding the wrong theory. And that is a certain kind of progress too, maybe less exciting, but in the end, we're part of a long ongoing journey, and we're not going to answer it in our lifetime. So that may be the best that we can hope for. Okay. Oops, I had a question and I touched it and it went by. What do we got? Okay, Abbas Safari asks, just try to imagine what space is, even if it seems too hard for you. If you manage that, then you will stop making things up and see reality, like the fish that realizes living in water. And I have sympathy with that comment. It is difficult to recognize the ubiquitous qualities of the reality you inhabit. It's difficult for the fish to recognize that it's in water. If it's never out of water, it has nothing to compare that experience with. So you begin to become unable to access qualities of reality that are so central that they're always with you. Now, when it comes to space, our intuition is molded by thinking about things in space. It's very hard for us to think about taking away space the way we can think about taking away water for the fish. But the nice thing is, there are mathematical models which do take away space, which do allow us to develop our intuition for at least the possibility of removing space. So if a fish were able to do that, an Einstein fish, what would you call that? Fishstein? I don't know. So if there's a Fishstein, really brilliant physicist, I think that's Lenny Suskind's combination there. So if Fishstein is this brilliant physicist and comes up with this theory that allows you to imagine a reality for the fish world that doesn't have water, it would open their minds. And we've kind of done the same thing in the world with space, but that doesn't mean our theories about space are the be all end all, that they're the final description. But we've taken your comment to heart, and we do try to imagine a reality and a mathematical description of that reality that does not rely upon a pre-existing environment. So what Fishstein did for the physicists, some in our world have done for us. Let's see, what else? So Bonnie says, I think the great professor is losing it, LOL. I hope I'm not. Maybe that was a little too off the deep end in that description. Let's see what we got. Some good questions coming through. Indy's bike, is gravity in another dimension? And I think the answer to that question is yes. Well, let me qualify it. No, let me just, I'll be quite general. I think the answer to that is yes. Our understanding of gravity, as you may have noted from the episode I did on Einstein's general relativity, is that gravity is associated with the geometry of space-time, the warps and curves in colloquial language. And in that sense, once you realize that there's this intimate association between space-time itself and gravity, gravity is nothing but the geometry of space-time, then you realize that if space-time has more dimensions than the ones that we know about, then gravity will be in those dimensions too. So that's the sense in which gravity is a universal quality of reality, at least reality that is in a phase that has space and time, because the geometry of that environment, the geometry of the whole environment, including all the dimensions, is really what we mean by gravity. And that gives rise to some interesting implications, because the other forces, the electromagnetic force, the nuclear forces, they're not as universal. They're not associated with the warpage of space-time. And therefore, you can find yourself in at least a theoretical possibility that the electromagnetic and the nuclear forces might be confined to certain regions of space-time, whereas gravity extends throughout all of them. And there are theories that have made use of that idea. You may have heard about the brain world theories, brain as in B-R-A-N-E, not B-R-A-I-N. And those theories imagine that we live on a membrane, a three-dimensional membrane, hard to picture, but use a two-dimensional version. It'll be just as good. Imagine that we lived on a kind of two-dimensional membrane floating within a higher dimensional space-time environment. That means that everything that we know about would exist on this membrane. So gravity extending through all the dimensions, we would have some of it because we, after all, are part of that space-time expanse, but the electromagnetic force might only live on our slice. The nuclear forces might only live on our slice. And that disjuncture between where the forces live, in principle, can give rise to some very interesting theories that people have developed. So yes, is the short answer to that question. 5:30, we're getting on time here, although my wife has not asked me about dinner and the kids have not yet. So I don't know, I guess I'll talk a little bit more. Krishna Raval, is it possible that you would give a course on general relativity like you did for special relativity? And I would love to. And of late, I think because people are at home more, is my guess, I've had more and more people encouraging me to do that. I love doing the special relativity course. And again, I've already mentioned him once before, but I got to mention him again. So Josh Zimmerman did all the visuals for that course. And, there are hundreds of animations in the special relativity course because I wanted it to be deeply visual. I think that's really, really understand things. But as you can imagine, it takes a long time to create those visuals. So to do such a course for the general theory of relativity would require developing a whole new set of visuals. And it just takes a lot of time. It takes a lot of money, right? Time and money are intricately interwoven. So we'd have to raise money to do that. We'd have to find the time to do it. But I am thinking that with this lockdown, and if this happens periodically, I hope it doesn't, but if it happens periodically and I find myself here, we're thinking of setting up a little studio here that would allow me to make headway on those kinds of projects when I'm restrained from working on other things that would require the world to be more opened up. So that may be a tiny silver lining. I don't mean to frame it that way. In fact, let me take that back. I don't want to frame it that way at all. That may be one of the things that I'm able to make headway on going forward, and I'd love to do it. So keep an eye out. Again, I mentioned World Science U is relaunching in a week or two or three. I'm not sure what the answer to that is, exactly when, but keep your eyes out for it. The special relativity will be there, as will the master classes and some other additional content as well. But you should sign up. Look, you should sign up to World Science Festival's YouTube thing, right? I think am I pointing at the right spot? I don't know. I think it's someplace over here. I'm guessing right now. Because that's where you can really be kept aware of everything that we're doing. World Science U also has its own YouTube page. We don't use it as much. You might want to sign up to that. But yes, it's conceivable that I'll do a general relativity course. I'd also like to do a quantum mechanics course. Those are the two other ones that I really, really would love to bring out to the world in a visual and mathematical way to try to make these ideas as clear as possible, from my perspective. So I hope so. But, life is short and you have to make decisions on what to do, especially on a kind of monster project like creating a full general relativity or quantum mechanics course. Okay. What else have we got? Well, there's a question that keeps coming up, and I better answer it because it will keep coming. So, Danny's smile. How can a gravitational field escape a black hole? So I'm going to answer your question, Danny, so you can stop asking it. I've seen it like 1,000 times rolling by. So I would say that a gravitational field doesn't escape a black hole per se. Rather, what we learned from Einstein is that the environment around a massive body responds to the mass energy of that body. And a black hole has mass energy. Think about all the stuff that fell in. So that mass energy of the black hole is influencing the environment of the black hole. And that's what Einstein tells us. It's not that if I have an object, gravity is escaping it. It's not that gravity is escaping the Earth in the sense that I think that you have in mind. It's rather that the Earth is impacting its environment in a manner dictated by the Einstein field equations. So when you write down the Einstein field equations for the, say, Schwarzschild solution, that solution solves the equations of Einstein outside a spherical body like the Earth. It doesn't, you can go further and talk about the interior of the Earth, but to understand the gravitational field that the Earth creates in its environment, you never talk about Einstein's equations inside the Earth. Again, not that you can't, you can. And you can connect the solutions together and so forth. But if you want to know what's happening outside the Earth, Einstein allows you to solve his equations outside the boundary of the Earth. Similarly for a black hole. If you want to understand the gravitational environment that a black hole creates exterior to itself, you solve Einstein's equations in the exterior realm. And you don't have to talk about anything crossing the event horizon of the black hole. Okay, I hope that gives some insight in there. So Ridgen says, bye, Professor. I got to go to sleep now. Take care and stay safe. Good night. Sweet dreams. Ridgen, thanks for joining us. Dang Joes asks, if gravity isn't a force, why are gravitons necessary? And what you're mixing in that question are two descriptions of gravity. In the classical description of gravity of Newton, the gravitational description involves something called the force of gravity. F equals g m1 m2 over r squared, the force of gravity. Einstein comes along and changes the description a little bit. Gravity, well, not a little bit, a lot of it. Gravity is associated to the geometry of the environment that a body creates. So now it's even a slightly different language. It's warps and curves and objects traveling along geodesics. Hey, I never did the geodesic equation. Oh, God, I should do that one. But the third description in terms of gravitons is a quantum mechanical description. Newton and Einstein are both classical descriptions. In the quantum mechanical description, we do envision that gravity is communicated from place to place in much the same way that electromagnetism is communicated from place to place. Electromagnetism, photons carry the electromagnetic force. We believe, but we've never detected, but we believe our refined theories suggest that gravity quantum mechanically is communicated by gravitons. Spin 2 massless particles, whereas a photon is a spin 1 massless particle. And that's the natural quantum mechanical language. And all of these languages are useful. And you need to apply whatever language is most relevant to the kinds of questions that you are asking. If you want to know about the bending of starlight by the sun, use the general theory of relativity. The curved trajectory is the one that observations confirm. If you want to launch a rocket ship to the moon, use Newton's description of the force of gravity. Good enough and easier to use to plot the trajectory to the moon. If you want to understand the gravitational interaction between two electrons as they scatter off of each other, then you want to use the quantum mechanical description of gravity with gravitons going back and forth between the electrons. That's something that string theory in principle provides us. And that's controversial because not everyone believes that string theory is the right quantum theory of gravity. But that's the kind of question in which a quantum theory of gravity would be a useful way of talking about the process. Also, clearly talking about the Big Bang and the center of black holes. Those are extreme realms where you need quantum mechanics and you need gravity. Therefore, you need a quantum mechanical description. Okay, a few more and then we will, I guess, wrap it up. Let's see. T-Bald. Oh, T-Bald. Dear Professor Greene, I hope you're doing okay. I am. I apologize for frequently asking the same question. No problem. I was just joking. But why is having a unified theory so important? And T-Bald, I would tell you that there are some people who do not think it's important to have a unified theory. Freeman Dyson, who I hope you know that name, he is one of the influential physicists from the middle and late years of the middle, 50s, 60s, 70s, 80s, 20th century, of course, played a vital role in the development of quantum electrodynamics, has a lot of creative ideas. The Dyson sphere, you heard about that? This way of capture a future civilization capturing all the energy coming out from its star. Earth only captures a little part of the sun's energy, but if you had the Earth part of a sphere that would not allow any of the energy of the sun to escape into space, that would be a much more efficient way to go forward. Anyway, so Freeman Dyson, serious guy, does not think that a unified theory is really necessary. He has suggested that maybe you use general relativity when gravity is the dominant influence, for stars and galaxies. Use quantum mechanics when you're way down at the small scale of particles, electrons, neutrinos, and things of that sort. And he says maybe the blending of quantum mechanics and general relativity into one unified whole is not only unnecessary, it doesn't exist, just wrong. For instance, he would even suggest that the notion of a graviton might be wrong, because that comes from blending quantum mechanics and general relativity. And Dyson may have been right in that perspective. I don't agree with that. I think most physicists do not. When I think about the deep interior of a black hole or the moment of the Big Bang, I know that our equations break down because they lack the ability to deal with those extremes of high energy, high mass, and small size. And it would seem that a quantum mechanical theory of gravity would be able to handle those situations. So that's why we're driven to find this unified theory, this quantum mechanical description of gravity, blending the large and the small, because we really want to understand the moment of the Big Bang. We really want to understand the singularities, which I've discussed already today inside of a black hole. But does that mean that such a unified description exists? Maybe not. Maybe there's another way to understand these extreme realms that doesn't unify gravity and quantum mechanics. As Steven Weinberg has emphasized on a number of occasions, the universe is under no obligation to please theoretical physicists. We theoretical physicists who imagine in the guise of Einstein, using the same perspective that he had, that there's got to be a single framework that blends all of the disparate explanations of the world emerging from physics, puts them all together into one unified whole. We believe that that should exist. We feel that it should exist. We have an aesthetic drive to put it all together into a single unified package. But just because we want it doesn't mean it's real. And maybe one day we will recognize that this drive toward unity was misguided, that there was another way of understanding these extreme realms of the Big Bang and black holes, and it had nothing to do with unification. Is that possible? Yeah, definitely possible. Are we ready to give up on unification? No, not at all. So Sai says Weinberg is an atheist, brilliant guy, much more than Dyson. Well, I don't want to compare Weinberg and Dyson. Weinberg is an atheist. Maybe, or is he an agnostic? I don't know. Who cares? It's a nice observation. I'm not sure why you're telling us that, but thank you. Okay, what else? I am asks, where do quantum and classical gravity need to be blended? And that's basically what I was mentioning before. You really do need to blend them in realms that are outside the domain of Newton's or Einstein's description. And Newton's and Einstein's description are unable to accurately describe what happens when the masses are really big and the sizes are really small. So any situation where the mass gets too big or the size gets too small is one in which quantum mechanics and general relativity need to be brought together. And it's really the conjunction of the two. A lot of mass in a small size, a lot of mass gravity, small size quantum. If that's your situation, you need them both, gravity and the quantum. You need quantum gravity. That's that's at least one way to think about it. Okay, Anas asks, could there be a fifth fundamental force? Absolutely, absolutely. In fact, there has been chatter of late about data suggesting another force. I don't know where that stands at the moment. And in the past, such chatter has gone away. But even in a theory like string theory, I should say, in string theory, there are many more than four fundamental forces. The other forces in string theory often only emerge at very, very high energies, well beyond the reach of today's accelerators or even any conceivable accelerator that our species is going to build. But you should know that fundamentally, within the mathematical structure of certain approaches to string theory, there are all sorts of other forces. They just aren't relevant at the low energy environment that we inhabit. But they're there in the equations. So an emphatic yes to the possibility of a fifth force. All right, what do we got here? 544. I'd like to break our previous record. Have we broken any previous records? What's the longest we've ever done on this Q&A? I don't know the answer to that. Maybe someone does. But I'm gonna go a little bit longer, as long as there's no tornadoes today. Nice day out here. And when I finish this session, I've got to immediately start cooking. I'm not in the mood to start cooking right now, so I'm procrastinating on making tonight's dinner. All right, you're not all that interested in that nonsense, so let me get back to physics. Reverend Jonathan Barlow Gee asks, Brian, can tachyons, faster than light particles, actually be the force-carrying particles of gravity? And the answer to that is no. The force-carrying particle for gravity really needs to be a massless spin 2 particle. If you look at tachyons, they're particles that actually have imaginary mass traveling faster than the speed of light. And they yield all sorts of issues of consistency that, you can stand on your head and maybe make them work. But most physicists do not take tachyons too seriously. But most physicists do take the force of gravity and gravitons quite seriously. All right, let's see. Multiplier fan is saying, how are you? I don't know if that's to me or to the group. I'm doing well. I'm having a little bit of sore throat issues, as you can tell. But let's see. I am says break some records. All right, I think we're on the verge of that. Alexandra Cara Raymond asks, is it tofu again? I eat a lot of tofu. Yeah, I'm pretty sure it's tofu tonight. We are so low in our food stocks right now that tofu, I think, is the only thing that is left. What will it be? It will be tofu and homemade black bean sauce, a little bit of rice, probably maybe a little bit of cold sesame noodles with it too. My son loves those. So the record was 2 hours and 44 minutes. We've now smashed that, I think, with 2 hours and 46 minutes. But Farah asks, what do you think of the series Genius? And I only saw the first episode. Well, not episode, I guess. By Genius, you mean that series, I think, that had Einstein, like a 10-part series. I only saw the first episode of that first incarnation of Genius. And I thought it was, as a film, really well done. It was captivating. It focused more, obviously, on Einstein, the man. The opening scene. Wow, Jesus. Einstein, the man, as opposed to Einstein, the scientist. And I think people find that quite interesting. I found it a nice contrast to the approach that we took in our PBS special, the one that I've mentioned from time to time. Light Falls, the live stage work that we had. It was broadcast nationally in the United States. I don't think it's been broadcast anywhere else in the world. We have to work on that. I'd like it to be broadcast elsewhere. But that focused much more on Einstein, the scientist. And that's the story. Look, I think all the stories are interesting, but the one that really captures me, obviously, as a physicist, is how radically he changed the world. One guy, in the span of a single lifetime, changed so much of our thinking. And to me, that's the inspirational story. And yeah, I'd love to know more about Einstein, the person, and that's good. But for my taste, it's really Einstein, the scientist, that really gets me fired up. So Junis Eunice asked, did Einstein's wife help him with the math? Um, that was something that was said by people during a period of time, that Mileva Marek, I'm not sure how to pronounce her last name, so correct me on that. That's how it's spelled. That Mileva helped Einstein with the mathematics. Now, Mileva was good, apparently. She was a fine physicist, did well in school. There's no evidence that she had the genius capacity of Einstein. And I'm pretty sure that subsequent research has debunked the idea that she was really the force behind Einstein's discovery in special relativity. There's really no evidence, as far as I know, for that story. Obviously, it would be an interesting story. It would be a romantic story. It'd be like that film. Was it called The Wife? Was that the film in which the wife of the writer who won the Nobel Prize in Literature, she actually wrote all the books? Was it called The Wife? I don't know. May have been, or maybe I'm talking about the wrong film. Somebody tell me if I've got that right. But that would be the story, of course, in this case. Maybe that rumor of Mileva was the inspiration for that film. I don't know. But there's no evidence, as far as I know, that Mileva is behind the math that allowed Einstein to come forward with special theory of relativity. Marriage, someone tell me, Spectre 11. Marriage, thank you. I don't know. Okay, thank you. I trust you more than I trust me. DM, are there any theories about what the singularity that may have existed before the Big Bang was? And there are many theories. We've discussed some of them here on various occasions. There are bouncing cosmologies where we are living in the aftermath of one cycle in what might be an infinitely long progression of cycle after cycle. Expansion, contraction, bounce, expansion, contraction. So the Big Bang singularity may have just been a moment between the previous period of contraction and the subsequent period of expansion. That's one possibility. There are other theories, even in string theory. There's an idea that people worked on. One of the founders of string theory, Gabriele Veneziano, worked on a pre-Big Bang scenario for a number of years, in which the universe would have, in some sense, begun big in the infinite past, and then in some sense, the right frame of reference, it would have collapsed down, and then not bouncing in the sense of going over and over again, but it would have had a prehistory. Our development would have had a prehistory in the far past. So people do write down theories. They develop these ideas. They try to analyze the singularity, try to make sense of the Big Bang, and some theories claim that they have. There's no consensus, though, that any of these descriptions are the right one. Prayag Dash goes to the free will question. I'm going to put that off, Prayag, if you don't mind. I've answered it before. It's in chapter 5 of my book. Again, I'm not asking you to buy it. Get a bootleg copy, read it. That really captures with precision my perspective on free will. And again, as I mentioned before, anybody wants to take my class, I wish I could offer it for free. Maybe there's a way to audit it for free. Some are taking it for credit. It starts next Tuesdays and Thursdays from 6 p.m. to 9 p.m. That may be too late for some of you guys who are in other countries. But I'll be talking about that in detail there as well. And again, it's not that I don't want to talk about it here. It's just that it's 8 to 6. It's almost 6 o'clock, and I think it'll take us too far down that rabbit hole. Maybe this is a good question to end on. It just went by. Where'd it go? I don't know. There's some question about an ultimate truth. I liked it, but now it went by too fast. See if I can find it again. Trying to find it. I can't seem to find it. Whatever. I guess I'll move on. Looking for the final question. This isn't the final one. Do I know Robert Lawrence Kuhn? Yeah, I do. I've been at conferences with him. He's a good guy. Really curious about deep questions. I like him a lot. What is M theory? We sort of already did. The M theory is just string theory on steroids. String theory done with a greater degree of mathematical precision. That's really what it is. So Brian just debunked the Born-Guth-Vilenkin theorem. No. So that's no. The Born-Guth-Vilenkin theorem tells us that if you're going to follow any trajectory far back, you're going to encounter a singularity. But it's not that every trajectory hits that singularity on the same singular surface. So you can have trajectories that go farther and farther back. And again, that's only in the context of the assumptions made in that theorem. So no, that is not my point. Let's see. Oh, here's one. So Samir Kadkatkar. Sorry. Is there one single ultimate truth? What is your opinion? I think that'll be my final question for today because it's nice and philosophical. And I don't think there's a single ultimate truth. I think there are many truths. I think the notion that truth is a singular essence or quality has led to much strife in the world, much dissension, much unnecessary bloodshed. I think that there are qualities of the world that are objectively accessible. And what I mean by that is not that we can get outside of our heads. We already discussed that earlier. Everything that we know about the world is subjective in here. But what I'm saying is there are qualities of the world that if we attempt to access them, we will access the same thing. Like, as I said before, the mass of the electron, the electromagnetic charge on the electron, and so forth. But those truths are only one kind of truth in the world. And the patterns that we develop to explain those qualities of the world, be it the standard model of particle physics, be it general relativity, be it whatever, those are accessing one kind of truth, which is that objective third-party accessible qualities and patterns of the world. The inner kinds of truth, the subjective kinds of truth that we as individuals have access to through whatever, meditation, through introspection, through self-awareness, through inner experience, through the experience of music or art or theater or reading, literature or poetry, those truths are equally real. They're not truths that are third-party accessible. They're not truths that are available to everybody in the same way because they are deeply dependent on the specific iconic qualities of our own particle arrangement, the way our brains are configured, the experiences that we've had, the genetic makeup that we acquired from our parents. So those truths are real. Those truths are valuable. Those truths are a vital part of a complete understanding of what it means to be a human being living in this universe. And those truths are different for each of us. And so in that sense, the totality of truths needs to be forefront in people's minds. So it's not that your God is better than my God. It's not that your theory about consciousness is better than my theory. It's not that your art is better than my art. It's the recognition that we are all on a journey to better understand ourselves, to better understand the world. And we get that better understanding through a variety of sources. Physics is one source. It answers the kinds of questions that we have been primarily focusing upon here today. But if somebody else was in this chair and they were talking about the truths that emerge at higher levels of understanding, the truths, say, of biology or chemistry, the truths of psychology or philosophy, the truths of art, the truths of anything else that we use as a tool of investigation into the nature of reality, those are vital truths. Those are not truths that physics directly provides to us. And the truths that also come from religious exploration, from conscious introspection, vital part of the story too. And those are the stories that we as individuals tell. Those are not stories that we have objective descriptions that we can all agree on because they're accessing qualities of the world that we all are able to touch in one way or another. So in answer to your question, I do not think there's one single truth. You have to recognize that there are many truths, many valuable truths. And the beauty of life is that we are equipped to experience those truths, to pursue those truths, and in all their wonderful, varied spectrum of possibilities. That doesn't mean that they're qualities of the world that aren't amenable to factual discussion. Are there qualities out there that absolutely science can give us insight into, like climate or viruses or things of that sort? Yes, not open to opinion or discussion at this stage of understanding. But are there other truths that are much more fluid and flexible and much more sensitive to the individual? Yeah, and they're equally important. All right, with that, I think I'm just about done. We're at 5:59, so I don't know, it's close to 3 hours of conversation, maybe. I hope you've enjoyed the time that we've had together. Again, as I mentioned at the outset, your daily equation will be a little bit less frequent. I'm going to still try to create some episodes, so look out for those. And I'll try to do this next week. These sessions are fun. Again, I may be doing a Reddit Public Access Network discussion next Friday at 2. So if you want to join us at 2 o'clock for that, and then we can segue into this one at 3 o'clock, that will be a possibility too. Again, follow me on Twitter if you sort of want to keep up to date on the things that I'm doing. I have no means of connecting with you except during these sessions. It'd be really useful if I had a confidence that if I wrote down something on Twitter, like I'm not going to do a daily equation today, or I'm not going to do a live session, that I would reach you. So follow me on Twitter. It's @BGreene. Follow me on Facebook if you'd like. A lot of stuff I post there. I think it's B Green. I don't know what I am on Facebook. Sorry, but easy to find. And also subscribe to the World Science Festival. I think this is the right hand. It's always confusing. I think this is pointing at the subscribe button. I hope it's there on the screen. So sign up, and we will connect again sometime during this week, hopefully with new episodes of your daily equation. If I can get to it, I will try. Again, it's my first week of teaching. I may not, but certainly by next Friday, we can join up here again. All right. Thanks for the questions. Enjoyed it. See you guys later.